Okay, it's fine. Okay, now it's registered. So it's my pleasure, yes, just to introduce Jordan Kuhle for this first talk of this afternoon. And we talk about solar cells and the application for small sat and CubeSat propulsion. So you have 30 minutes and 10 minutes of question and comments. Please, Jordan.
Yes, thanks. So today, thanks everybody. So today I'm with Luis, the CEO of Gamma, that will start the presentation by talking a bit about the company and the goal of the company. And then I will talk about the technical part and the development of the solar cell in Gamma. So I will let Luis start with the first part of the presentation.
Thanks a lot, guys. Thanks a lot for your confidence, and thanks for the time we're having together today. So I'll present quickly myself and the company, and then I'll go through our presentation, and then Jordan will go through technical details. So I'm Luis, I'm Gamma's CEO, I'm 29. Today, Gamma is a team of roughly 12 to 13 aerospace engineers. We're based in Paris, and we're working on solar cells. The project was born thanks to a video I watched of Light Sail 2 that was launched in 2019, I believe it was. And then there was on France Culture, a great show with people talking about solar sailing. And I said to myself, there might be amazing opportunities for propulsion with solar sails. And as I wrote my PhD thesis in space law, I got especially interested with applications in low Earth orbits. But then I started also looking at deep space applications. And I thought that maybe we could have nanosatellites equipped with solar cells as a low-cost solution to have deep space access and, of course, to unlock the solar system. So as you may see on your screen, Gamma, we are building solar cells for deep space. At Gamma, we came to the conclusion that space is the final frontier and that we've explored so little of our solar system and indeed so little of our universe. And we believe that there are a lot of scientific and commercial opportunities with exploration. So Gamma is a French-based company that is really laser focused on exploration of the solar system with solar sails. So as you may know, today space is becoming finally accessible thanks to a large reduction in launch costs and thanks to cheaper and smaller satellites, nanosatellites. That's the subject of the presentation today. And of course, this has generated an explosion of commercial activities with more and more funding injected every year in the space activity. We came to the realization that most of the satellites that were launched today in space are actually launched in low Earth orbits, roughly an altitude of 500 kilometers, sometimes higher, sometimes a little lower. And that so little spacecraft were launched beyond the Earth-Moon system. And this is mainly due to the fact that it's easier to launch in low Earth orbits and then to have, applications in low Earth orbits. As soon as you want to go deep space, you have to have an injection for deep space trajectories, and you have to have spacecraft that are equipped with deep space components. And this is, of course, very complicated today with nanosatellites. But the thing is, and of course, because in-space propulsion remains expensive and limited, spacecraft having to carry their own fuel, either for maneuvers or for trajectory corrections, etc., etc. And so at Gamma, we're working on allowing free and infinite propulsion for spacecrafts. We're building solar cells, and our project is to build the largest solar cells ever flown. We have a first launch coming next year in 2022. We'll be talking about that. We will be launching a 6U CubeSat equipped with a 110 square meters solar cell. And the project with that first launch is to demonstrate the deployment system of our solar cells, because unlike most of the solar cells that have flown today, especially NeoScout that's going to fly in a couple of months, Light Sail 2 and NeoScout and NanoCell D and Icaros from Japan, etc., etc. Most of the solar cells today are equipped with booms, and we want to use the centrifugal force to deploy the largest structures ever and to have the largest solar cells ever. So we're having our first launch next year. We're moving quite fast. We're using the sun's infinite resources in space. It's a concept that has been proven. And our project is to sell in the upcoming future solutions where laboratories, universities, space agencies, emerging space nations, or private actors will be able to just insert some payloads, and we will take care of the navigation of the solar cell, the launch of the satellite, etc., etc. So our project at Gamma is to actually sell missions to potential customers. We've identified a few customers, and at the moment we are talking with a few partners. We're very happy to be helped a lot by different laboratories, by different agencies, especially CNES. So we're moving quite well, and we're hoping that we can show that solar sailing is a great way to navigate in space, and that it's propulsion system that is going to be one of the 2 or 3 propulsion system next to chemical propulsion and electric propulsion. So that's our very goal, showing that we can do deep space mission at low cost with nanosatellites equipped with solar cells. I don't know what else I should tell you. This is our deck. So at the moment we are raising funds for this journey. We are raising fund with private investors, with business angels specialized in space mostly. We're also raising money with public agencies, especially in France, an organism that's called BPI, Banque Publique d'Investissement. We are being helped by a few people in the project, and now the team is working and things are going on pretty well. Maybe I let Jordan have been talking for, I don't know, 5-6 minutes. I'll let Jordan maybe start with the technical stuff, since that's where we're all here for. And of course, I'll be here at the end for the questions. So thank you very much for your patience and for watching this presentation.
Thanks, Luis. I will just switch to my presentation. So thanks, Luis. So now to talk about how we will make that possible, how we are going to what is our plan to make this project and all this vision possible. So to show you a bit the timeline and the different projects we have in Gamma, we are planning for now 5 different missions. Today we will talk about the 3 first ones that are the true planned missions, and the 3 missions that will help us to demonstrate our technology and that will help us to get to a product that is reliable. And those 3 first missions are Gamma Alpha, which will be launched next year in 2022, July, August 2022, to be exact. The launch is already booked, and we are working on for this mission. I will talk about it later. Then we'll launch Gamma Beta. So Gamma Alpha will be focused on the deployment of the solar sail. The first part of solar sailing is to come from a stored configuration to a fully deployed configuration with a really thin film of solar sail. So that's the first challenge of solar sailing that we will demonstrate with Gamma Alpha. And the second mission, Gamma Beta, will fly also in LEO, or maybe a bit higher if it's possible, according to the launches. And the goal of this mission will be to fly almost the exact same size of solar sailing with the same size of satellite, so a 6U CubeSat, as we said earlier. But this time we'll focus on the control of the solar sail to make it possible and to work on different control laws and to work on the different way to control those really big thin film in space. And then Gamma Gamma, that will be the third mission sent in 2025. That will be our first true mission that will target deep space object, so higher than GEO. And this mission will aim to demonstrate all the technology that we already developed, this time in deep space. So to start with Gamma Alpha, the goal of this mission is to deploy in low Earth orbit, to be exact, in a SSO, sun-synchronous orbit at 550 kilometers altitude, launched by a Soyuz in July 2022, as I said before. And the goal is to deploy 100 meter square solar sail. So in solar sail, the goal is to always improve the area over mass ratio, which is directly linked to the acceleration that we will produce to the spacecraft. And so basically the goal is to have the biggest solar sail possible for the lowest mass possible. And so for this mission, we'll get a area over mass ratio of 9, which is among the best already built by the other solar sail. And the first produce will be 0.5 millinewton. So for a mass of the spacecraft, which will be approximately 11 kilos. the space. So we are developing only the payload of the spacecraft. We are developing only the solar sail film, so itself, the film itself, and the deployment system, which is a bit tricky because I said, as Luis said earlier, we are using the centrifugal force to deploy the sail. It came from the idea that we want to always improve our area over mass ratio, and that we discovered that the only way to have the biggest ratio and the biggest sail ever made is to get rid of all the structure that could be used for deploy the sail. Of course, it leads to a lot of challenges, and that's why we are developing Alpha, because we discovered that with this technique of deployment, it was cheaper to test it directly in orbit and to send a mission fast in orbit to test this and to validate this deployment system than working on it on Earth and try to reproduce and to create an environment on Earth available to test our solar sail. So we are developing this system, and we are using a platform, the M6P platform from NanoAvionics. So a 6U platform. We are working with NanoAvionics. So we are developing the hardware of the payload. They are developing the hardware of the satellites, and we are developing the software, both of us, to control the sail and to make it possible. The team, today we are approximately 11 in the team, and the technical team is made of 3 different sub-teams, let's say. The GNC first, GNC team, so for guidance, navigation, and control, which is a really important team, and because this will be the biggest challenges of the following years for the company, as the control, as I said, is really complicated for solar sails, and we still have a lot of uncertainties on how it will be possible to control those big film in space, and how it will be possible to do it in deep space. It's also really important because the trajectories are very specific for those kind of propulsion, as the thrust is different at each point of the orbit. So we have to be really aware of the GNC for those kind of missions. The second team is the system engineering team, which is also playing the role of managing the project and making sure that everything is working fine inside the system and also with the platform. And then we have the mechanical engineering team, which is responsible of the design of the payloads, the system, the deployment system, the actuators, and the assembly, integration, and test of the full payload, and also and mainly the film itself, the sail itself. So to have a quick chat about the development cycle of Gamma Alpha, we are currently in C phase. We passed PDR last July with a team of CNES that help us with the PDR. And so now we are running for C phase of the payloads, and we are developing at the same time the satellites, which is in B phase with NanoAvionics. And the PDR of the satellite should be in October of this year. We will be able to make a qualification sequence during this winter, and then to integrate the payload and the final solar sail in March of this year, to have a launch on July of 2022. So to talk about how we deploy the sail, it's actually a bit tricky, because then we have to come from this stowed configuration to this deployed configuration, and we are kind of following the same methods as Icarus, which was a Japanese mission that also deployed a spinning solar sail. And we are trying to do that with a smaller space, smaller mass, and less resources. So the goal is, the first sequence of deployment will be to get rid of the structure. And so for this, we will extrude the payload from the structure. So this is the first part of the deployment. Then when we extrude the payload, so we extrude it with, thanks to some springs that extrude the payload, and we liberate the springs with some actuators. Then the second phase is to deploy the diagonal of the sail. So it is made by the rotation of the central part, so the yellow part that you see in the schematic. And then we deploy little by little all the diagonals of the sail this phase is long. It takes some days to deploy all the diagonal of the sail. And the sail is kept folded by the 4 red rods that you can see in the schematic also of the schematic. Yes, and so we deploy the diagonals, and when the diagonals are fully deployed, so we will check with cameras and a lot of sensors that everything is going fine and for troubleshooting. And after this phase, we will finally liberate the 4 red rods that I showed you before, and it will liberate and extend the full sail. And this phase will be really fast. It will be some seconds. But so the full deployment phase from phase 1 to phase 4 will take approximately 1 week, as you can see in the graph in this slide. So it's a long process. Why? Because we are rotating the satellites in the axis of the biggest phase of the satellites. And so we don't have that much resources, as it's a small spacecraft. We don't have that much torque. And so we need to control this torque and to keep it really low, sorry. And this means having a rotational speed quite low. So we are rotating at 6 RPM approximately. So that's why we are deploying the sail that's slowly. And also because we want to monitor it exactly, as the main mission of Gamma Alpha is to focus on monitoring and demonstrating the deployment sequence. We want to monitor this deployment as much as possible. Then, as we can fit with these results, this application, this experimental result, with our models that we are developing also numerically, and then we can improve our numerical models with these results. So you have here a schematic at scale of what it will look. So this is a 100-meter square sail that will be, and you have the small spacecraft in the center, the 6U spacecraft in the center. And so you can see on the right that the sail is actually made of 4 petals. So we are not building just a square, we are building a square made of 4 petals of 25 meters square of solar sail. So how the material, about the composition of the sail. So the sail is very thin. We are using a polyimide called CP1, which is 2.5, the thickness of this material is 2.5 microns. So it's really thin, really thin. And we are metallizing these materials with a 100 nanometer aluminum sheet. So in one side, the polyimide and the sail is metallized with 100 nanometers of aluminum, approximately. And so this polyimide, we have access to rolls of 1.5 meters with this. And so we have to assemble this sail. And this is one of the challenges also of Gamma Alpha, is also the assembly and the actual integration of this thin film that has to be well folded and well rolled to be well deployed. So as I said, the sail material, we apply rip stops to stop rips. As in space, we will have some meteorites, some object that will impact the sail for sure. So we, instead of avoiding these impacts, we are just stopping the rips with rip stops that are basically some tape that will stop the rips. And we use eyelets for interface with the payloads. So to show you a bit the AIT sequence, we already tested it with a 15-meter square sail. So as you can see, we have 1.5 meter with this VDA coated CP1 roll. Then we cut them. We made them as we want, so the shape of the actual petal. And then we apply the rip stops with so that is basically tape. Then we fold the sail. This part is the most critical because the folding is complicated with those kind of materials that are really thin, and it has to be perfect because the best we get the folding pitch, the best deployment we'll get, and the more the biggest sail we can fold and roll in the spacecraft. And so we will be able to have a better area over mass ratio. So this is why we are working on ways also to improve our folding with machines, because as you can see here, it was made by hand to make it more accurate. And then the last part of the assembly is the wrapping. So we are doing the exact opposite of the deployment sequence. We are rolling it. We are making them diagonals and then rolling it back in the hub, thanks to a machine that helps us to keep the sail well wrapped around the hub. Then we can also keep we can have the best space saving and room saving in the spacecraft. So to conclude on the AIT part, we did some tests, we did some training sessions, and we are working on our protocols. And what we discover is that it's really long, especially the folding parts. And that's why, and we need big space, big clean room, big facilities to do that. And so that's why we need to work on facilities to integrate, to fold all those materials. And so one of our goals in Gamma is also to master and to be able to manipulate, to integrate, and then to use in space and to control in space those big thin films that can be used for other applications also, for example, antennas or whatever. We did some tests also. One of those tests was to test the behavior of the sail in vacuum. Everything went well, and then we deployed the 15-meter-square sail made of CP1, and we tried to monitor and to have the value of the exact centrifugal force that we need. And we are still working on some tests, especially a deployment test at low scale that we would like to do to validate our deployment system in experimental way. And now to talk about beta. So when we will validate this deployment, we will need to control the sail. So we'll start to control it in Gamma Alpha, but really a little bit, because Gamma Alpha will be a short mission. And so with Gamma Beta, we will try to test the control of the sail. So it will be the exact same mission of Gamma Alpha. We will try to get a bigger sail, but we will see what is possible. But the true goal of this mission is really to validate the sail control. And also we'll use this mission to add some features to the sail that I will talk about it later. So the control strategy with the sails, with the solar sail, we can accelerate, decelerate in space. But for this, we need to orientate the sail and to change the orientation really fast and a lot of time during, especially when we are rotating around the body that is not the sun. And so we need to be able to control those big structures. So the different steering law that we'll test in Gamma Beta are the following. So you have the on-off steering law, which is just basically being on, so facing the sun when you want to accelerate, and then being 0 degree according to the sun, so in the same direction as the sun, to don't decelerate when you are coming back to the sun side. And then you have the locally steering law, which is the best steering law in theory, because you maximize your thrust in every point of the orbit, but this one requires 180 degree rotation at one point of the orbit, which is really complicated to do with a 100-meter square with a super small satellite in the middle. And then the steering law that will maybe be able also to test in Gamma Alpha, which is the polar escape steering law, which is basically the best steering law for polar orbits. And basically it's just staying at 35 degrees from the sun. And it's the best, one of the best laws to get an escape trajectory from Earth. And then, so to have a quick chat about that, this is the Gamma Alpha expected lifetime that you see there. You can see that it's really short because of the super big surface that we get for small mass. And so the conclusion of this is that solar sailing is made for deep space application and for at least high altitude application. It's not useful to use them in low Earth orbit instead, or just for deorbiting devices, because you will never get out of the Earth's atmosphere. So the new feature that I was talking about is adding some LCD control devices that will help us to control the sail. So basically it's using a screen that will change opacity to change the orientation of the sail and to change the thrust in one part to change the orientation of the sail and to help us to actuate the sail. It will be also putting solar panels to get big solar panel surfaces, areas. And then we will work also on sail rigidification, as we want to reduce our spin rate The goal is to make the sail to rigidify the sail. Thank you. To reduce the spin rate. And then finally, Gamma, which is our first, that would be our first deep space mission. So we don't have that much information yet because it's still in a long time. But the goal of this mission will be, being the first commercial or scientific mission of Gamma, the goal will be to validate all the applications that we already developed, but this time in deep space, and work on control in deep space. And this mission will be then between a 12 and a 24U spacecraft. And the goal is to get to a 500 meters square solar sail and to get to an area over mass ratio of between 50 and 20. And then, the stress will be 2.5 millinewtons created. And just to have a quick chat about a software that we are developing, which is named Sextant, to stay in the sailing world. And so the goal of this software is to develop tools that will help us to develop solar sail. It's really focused on solar sailing and on deep space trajectories, because we discovered when we started the phase 0 and the mission analysis on Gamma Alpha that it was not, the tools that are existing today are not sufficient for our work and are not really compatible, with the solar sails, as it is a really specific propulsion system. We need to develop our own tool. So this is why we are doing Sextant. Sextant is in development phase now. The first version should be available next year if everything is fine. And so it will be a tool for solar sail simulation, mission planning, operations, and all of that with a cool user interface to make it better. Well, thanks to have listened to us. I think we are done. Either if Luis, you want to add something?
No, just very happy to be here with you guys. Do not hesitate if you have questions, and we're here to answer them. Thanks a lot.
Thanks a lot.
Okay, thank you guys. So now the paper is open for discussion and comments, please, in the audience. So we have one question. Maybe I can give also the.
I think it's administrative related.
Ah, sorry. Did not. Okay. Other question, comments? Yes, Stefan?
Is my microphone on?
Yes.
Okay. Yeah, thanks a lot, Luis and Jordan, for this very interesting talk. This is really great, really new for us. This is also quite new for our community. And this is the reason why we decided to include it in this workshop. And I'm really eager to see how you're going to develop and how you're going to make it feasible and to achieve what you have said. I have many questions, so I have some of them that we will have possibly another occasion to discuss. But how can you compete currently with all the more classical existing electric propulsion technology? What are the pro and the con and the advantage drawbacks?
Yes. So I think first, we are not trying in the first part of the company. We are not really trying to compete with the other propulsion system because we know for competing with those propulsion systems, we would need really big areas and that are not really possible to build today. But what we want to do is to add device in spacecraft that will make able multiple target missions, or for example, to allow spacecraft to have an infinite source of propulsion, to get, for example, to sample Rotation missions and those kind of missions that needs a big amount of propellant, for example, for an electrical propulsion or for chemical propulsion.
And
Yes.
If I can add something, I believe we're not trying to compete, at least at first, but I think we will never be really competing. We're just complementary to other types of propulsion. So that's the first thing. And that's what I said in a quick introduction. We don't want that solar cells replaces chemical propulsion or electric propulsion. It could not. We just want to be another device that can also do other kinds of missions. And the second thing I'll add is it's kind of complicated to do deep space with chemical propulsion or electric propulsion on nanosats, especially like 6U or 12U. So there are solutions now, but they are limited since they have to embark some, some propellants. And there are lots of projects ongoing with, like refueling in orbits and on-orbit servicing, et cetera, et cetera. But what we believe is that for the nanosat revolution to happen in deep space, as it happened in low Earth orbits, we need a new type of propulsion, and that can be solar sailing. So I'll answer your question. First of all, we're complementary to other types of propulsion. And second, we really want to focus on small satellites where it's difficult to embark other kinds of propulsion because they are limited due to the propellant they have to embark, if that makes sense.
Yes, it does. It's really crystal clear. So, okay. Laurent, can I ask another quick question?
Yeah.
Or are there any other question in the audience, maybe? I don't want to lose all the time. The other question is about your deployment strategy that you well described using the centrifugal force. You want to test this on Earth before trying in space, I guess. But then you will have, of course, the effect of the Earth gravity.
Yes.
So how can you avoid that, or how can you minimize the perturbation due to the Earth gravity when you want to test the deployment strategy?
Yes, actually, it's a really good question because this is one of the big challenge we have actually to test and to build this first spacecraft. At first, we wanted to maybe use a zero-G flight, a drop tower, those kind of devices. The problem is that the availability of those test benches are really low, and we need to book those flights for 2 years before having a slot. And so it was too long for the development sequence that we have. And so this is also why we want to go fast in orbits. This is also because for us, it's an easier way to get to zero-G kind of. But we are trying to make a small scale deployment of this spacecraft and of this deployment sequence. And so the goal will be to try to compensate, to make it turn faster, to compensate the gravity kind of. And otherwise, we already did some deployment tests here in the office with using balloons to counterbalance the gravity. So helium balloons that are made to counterbalance the gravity, but it's still really complicated to well defined. At one point, it is representative. At which point it is representative of the reality. So we are developing this, and we are developing also a lot of numerical models on the computers using softwares and using also our own software, Sextant, to have the best representativity that we need. But this is why also Gamma Alpha will help us to fit these numerical models with the experimental results.
And if I quickly may add, there's also a phenomenon that as soon as you're in space, people consider you more. And since we're working on sci-fi tech and people, today we're pitching to so many investors and they're just thinking about solar sailing as a scientific way of exploring the universe. We wanted to be as soon as possible in space, first of all, to show that we can go in space. Second, to show our product will deploy in space. And thirdly, that it's reachable as a technology.
Thank you.
Thank you, Stéphane. I will ask myself a question.
Yes.
According to you, now, what is the limitation? What is the maximum of surface that you can do?
So the maximum surface that we can do. So first, I will talk about the boom system, because we started with a boom configuration, the one you can see in the background.
Mm-hmm.
That was the first prototype. a very long time ago now. So the boom system is limited by law of physics. And actually, NASA is working with boom systems, and they estimate the maximum deployable sail to 5,000 meter square sail with booms. And for rotational for spinning solar sail, the limit theoretically would be only the mass that we can get inside the spacecraft. So the goal is to have the best area over mass ratio, and our objective is to always get to the thinner and lower mass material to have the best ratio. So to answer the question that which area we can get now, theoretically it's infinite, let's say. It's not infinite because we will have a point where so far with the materials we have now, we'll have a point where the assembly of the sail is getting heavier than the sail, and so we will lose the area over mass ratio race. And so it's approximately around, now it will be approximately around 10,000 meters square.
And to give you a quick comparison, so the three most famous solar sails are Light Sail 2. It was a 3U CubeSat with a 36 square meters solar sail, a little more, like maybe 50, maybe no, 36, I believe it was. We had Icaros, which was a very heavy bus with a kind of small solar sail compared to the mass of the bus. And we have Neo Scout that's going to be launched with Artemis 1 on the SLS in a couple of months. And this solar sail will be a 6U CubeSat like us, but that will only deploy a little less than 80 square meters solar sail, whereas we'll be deploying a little over 100 square meters solar sail. So we're having the best ratio surface over mass for the 6U standards. And we're going, of course, to improve that because we want to go way higher. And thanks to the startup mentality we have, we can move fast, whereas NASA took, I believe it was 10 years to deploy and to develop Neo Scout. So we're trying to move as fast as possible.
Okay, thank you for the discussion, and thank you for the talk.
Can I ask a quick, do you have time?
Yeah,
very short one. Yeah, I have time, so I have time. Guys, a very quick one. What do you think about the idea of the strategy of using laser to provide the photon flux? Solar.
To be honest, Professor, that's why I created the company, because I believe the true breakthrough. It's also the name of the company which want to make that breakthrough starshot. But if we have solar sails with nanosatellites equipped with solar sails for deep space mission, it's good. We will be one suppliers among others. If we have the technology, and today it is used for telecommunication, to maybe in low Earth orbit use lasers, I don't know how it will evolve, or maybe from the moon, or I don't know how things will evolve in a couple of years. But if we can actually accelerate the sail at a true speed that will allow the solar system to become closer to us, we're changing. I mean, we become the new SpaceX kind of. I mean, it's a bit pretentious, but the true amazing part for us would be to use lasers and to have, like times of, I don't know, a couple of weeks for Jupiter and a couple of days for Mars. And of course you have to slow down after, that's another problem. But I mean, I'm pushing the company to work on that. They're telling me, no, Louis, it's already complicated to have big surfaces, to have the right software to navigate the sail. But I'm pushing for R&D on the laser propulsion, because that's the true game changer. And this will help not only the company, but it will change the way we inhabit the solar system. And that would be the amazing. We're all young, so we're all in our 20s, mid-20s. So, who knows? But that's our dream.
I'd like to say it before I die. So you have basically 30 years.
No problem.
Thanks.
Okay.
Thanks a lot, guys. Thanks a lot
also
for your enthusiasm.
Thank you.
Thanks.
Exactly.
Take care.
Thank you. Bye.
Cheers.
Bye.
Bye. So, and the next speaker is Denise Zolotukin from the George Washington University, and we talk about ion velocity increase in a two-stage microcat MPD thruster. So please, Denise.
Oh, can you hear me?
Yes.
Our group from the Micropropulsion and Nanotechnology Laboratory of the George Washington University is working on the research of microcathode vacuum arc thrusters for micropropulsion. Microcathode vacuum arc thrusters.
Yes, please. Sorry. Denise, please Can you share your screen? We did not see your presentation. Sorry.
Oh.
We hear you, but we did not see your presentation.
Yeah, I see.
Okay, sorry.
Oh,
Okay, now okay, good. Thank you.
so microcathode vacuum arc thrusters are plasma thrusters that are suitable for propelling small and lightweight satellites as CubeSat. In traditional one-stage configuration, with one discharge gap consisting of cathode and anode, they typically generate micronewton level of thrust with low thrust to power ratio. In order to achieve much higher thrust values, up to thousands of micronewtons, at higher efficiency, special efforts should be made. Recently, we proposed the idea that the MuCat performance can be enhanced by addition of the second stage based on magnetoplasma dynamic concept. Such two-stage MuCat MPD configuration allows increasing the thrust levels in tens of times, together with the growth of thrust to power ratio of up to several times. The concept doesn't involve lifetime limited cathode neutralizer, high voltages, and ion loss on the grid. However, the size, mass, and the shape of the second stage electrode still need to be optimized. Such experiments have been conducted in different configurations of the MuCat MPD thruster. We will talk on this configuration further. Here are our diagnostics. The velocity of ions was measured by a well-known time of flight method. We used two negatively biased grids separated by the known distance. Ion velocity was estimated by dividing the distances between the first stage thruster phase and the first grid, and the second grid by the corresponding time difference between the maxima of the first stage current and ion current signals from the each grid. This is a schematic of one of our first concept of MuCat MPD thruster. For the first stage, we used the MuCat with a coaxial cathode anode gap. Its plasma was expelled toward the entrance of the positively biased second stage fully metallic accelerating electrode. Both MuCat phase and the accelerated electrode small opening were located in the central plane of the magnetic solenoid, consisting of around 300 tons of copper wire powered by additional pulsing PPU. Due to interaction with external magnetic field, a Lorentz force was acting on plasma, providing acceleration toward the wide opening of the accelerating electrode and finally increasing the thrust. On the right figure, we see that the ion velocity rapidly jumps in about 1.5 times with increase of ion current from 0 to just 2 amps. Such a drastic growth of velocity is probably due to acceleration of ions by the magnetic field and the Lorentz force, but further increase in ion current to around 70 amps leads to a more modest growth of ion velocity, probably due to saturation of the magnetic field in the iron core. However, we see that the velocity decreases with the second stage voltage. This means that the concept should be improved. For such improvement, we replaced a magnetic coil by the permanent magnet. In this configuration, both the MuCat phase and the opening of the MPD electrode were now located in the end plate of permanent magnet with the magnetic field strength around 0.2 Tesla at its axis. On the right, we see that ion velocity without the magnet, it remains within 10 or 13 kilometers per second, which is typical for velocity of ions from copper cathodic jet. And this velocity very weakly depends on the MPD stage voltages. However, with permanent magnetic field, the ion velocity is at least in 1.5 times higher and significantly grows with MPD stage voltage. So here, brief conclusions devoted to the study of our thruster in configuration with fully metallic electrode. So two-stage MUCAT MPD thruster concept generally allows increasing the exhausting velocity as a function of the applied voltage. In configuration with thruster with pulsing solenoid, the ion velocity can decrease with the second stage voltage. Although this velocity still remains with the velocity remains higher than the velocity without the magnetic field. And in the best configuration that we achieved here in MUCAT MPD thruster with permanent magnet, the ion velocity grows with voltage on the accelerated stage and remains significantly higher than the velocity without the magnetic field. So I ask my colleague Ram to continue talk on MUCAT MPD thruster configuration with segmented electrode.
Hi, I think I cannot share my screen here. Well, I'll ask Dennis to help me out with this.
Yeah,
Thanks, Dennis. Thanks, Dennis. As Dennis mentioned, we wanted to. Can you go to the next slide, please? As we came to know that like there is some significant increase in the ion velocities, the second stage. So we want to check like at what size, what shape of the cone, and what power we are getting the highest maximum velocities. So we have conducted several experiments using this MPD segmented thruster. Dennis, can you please go to the next slide? So my configuration is looks something like this. We have a cone and we attach, which is like the angle of the cone is 45 degrees, and we attached rings, like electrodes in the form of rings. We have like four different sizes and four different places of the cone to check at what optimal distance from our cathode we are attaining the maximum velocity. And also I used a pulsing coil, since I cannot place a permanent magnet over the cone. So I kind of like wrap the coil around the cone to provide some magnetic field for the provide some magnetic field. Can you just go to the next slide? So here, this is my first stage ion velocities. The maximum current attained, the maximum discharge current attained is somewhere around like 49 amps. And the cathode I used here is titanium cathode. I used the same method what Dennis used for to calculate the ion velocities, like the time of flight method, to keep us on the same page and to check whether our velocities are matching with each other. So the first stage velocities is somewhere around like 26 kilometers per second. It's also matching with the literature review. When I take the titanium cathode, and then it's good. So here is my second stage ion velocities. If you see here, like the green, the ring 1, like the maximum velocity attained by the ring 1 is somewhere around like 100 kilometers per second. But while you compare somewhere around like 40 kilometers per second at 100 volts when I supplied 100 volts to the ring 1. But when I supplied this, when I supplied 40 volts to the ring 4, it attained 75 kilometers per second. So, but initially the velocity of ring 4, it started from 40 kilometers per second. So that like there is some significant change in the velocities from my first stage to the second stage. Also, but something weird I observed in my ring 2 is that like there is no saturation point. Though all the rings, like all the electrodes, attain some saturation point at the same voltage, but for ring 2 we didn't observe any saturation velocities. So we are trying to like check what is, if we are getting the same thing even on the thrust stand. So we are trying to do some thrust measurements experiments to check if we are observing the same thing even during our thrust in our thrust experiments. Dennis can go to this slide. This is how our thruster looks when it starts firing, like when there is no supply to the, like this is the pictures I've taken for ring 1, and this is what we observed for ring 1. When I supplied 0 volts, there is like no you can see the difference between the discharge, what is happening in my second stage. There is a very bright light, or like very bright discharge when this is my second stage. And when I supplied 100 volts to the ring 1, we had a very like a high blue, very bright blue. Dennis, can you go to next? So this is what we observed from our readings, from our measurements. There is some significant increase there is some increase in the velocities, ion velocities of our thruster, but with a function of voltage. The maximum velocities attained by our MuCat and PD thruster for each ring, it's not at the same point, but their saturation point is same at the same voltage. Also, we observed that these velocities are changing with respect to the magnetic field, like with respect to the magnetic field we are supplying to the MuCat. Thank you.
Thank you, guys. So we have 5 minutes. We have time for discussion and comments about the paper. In the audience, please. Is there any question? Stefan, yes?
Yeah, thanks a lot, guys, for attending the conference, presenting this interesting two-stage McCormack thruster. I was just wondering about how does the thrust to power ratio or the efficiency, I might have missed it, maybe you mentioned it, but how does the thrust to power ratio or efficiency changes when you use the second stage?
So basically, we didn't present this result in specifically this presentation, but it was published in our article in Physical Review E journal. So thrust to power and efficiency grows with second stage voltage only after some threshold. So we found that this threshold voltage equals to 30 volts. So below this threshold, there is no change in thrust to power and efficiency. But after that, efficiency in thrust to power grows up to, I don't know, maybe 15 micronewton per watt, something like this, from just several micronewton per watt in this range.
Christophe, you want to ask a question?
Yes, a small question. When you speak of 85 kilometers per second, does it mean also 8,500 seconds, or it is a similar question as Stefan?
It's yes, like 85,000 like meters per second. Yeah, and the power what we supplied it's not the power, the voltage basically here. I didn't calculate the power yet for this thruster because we are in the initial stages of calculating the ion velocities, and we want to check like how this varies even like with ion currents, and then we want to like calculate everything in detail. But yeah, for now, like we checked that I attained at the 85 kilometers per second. I attained at like 40 volts when I supplied 40 volts to my fourth electrode.
Okay.
Okay. I have myself one question about the cathode material. You were using titanium, right?
Yes.
Yes. And only titanium, or have you tried different type of materials?
We tried different type of material. We didn't try basically different type of materials. We are confined to titanium for now. But when I used copper, I only checked for my first stage, and it was like around 14 kilometers per second in my first stage. Yeah.
Okay, but only with the first stage. Okay.
Yeah, just like without any effects. It's only the thruster, like only the cathode and anode. That's it.
Okay. Thank you, guys. So I think that we can now move to the next speaker.
Thank you.
So the next speaker is Sherazad Barquero from Madrid in Spain. And she will talk about the preliminary test campaign of an ablative pulse plasma thruster for micropropulsion.
Yes, thank you for the introduction.
So you can share your screen.
Yeah. It's okay. Can you see it? Yes.
Okay, so you have 15 minutes and 5 minutes of question.
Okay. So we are going to show some preliminary conclusions extracted from the first ongoing testing campaign of APPT technology. And this is a challenge for the group because it's our first time working on pulse devices. And this promising technology for onboard propulsion for CubeSat is not without a problem or difficulties, mainly related with the complex physics behind the ionization of the and acceleration of the plasma generated, which involves many species and population, and also extremely high currents and short time scale. So to deal with this aspect are key aspects to try to improve the efficiency. So this presentation is going to be based mainly on showing the appearance of the discharge, and it's going to be supported by voltage measurements, photography, diagnostics, and also single linear probes, even though this is a very preliminary stage of this campaign. Also, the motivation of this initial approach is to identify and to be more familiar with the proper diagnostics of these kind of technologies, and also to face the difficulties that we are finding. First of all, we are going also to summarize up the triggering problem of APPTs, because this is not a straightforward at all matter. So this work is framed by the Martin Lara project, which is a regional project principally funded by the community of Madrid. EP2 is the responsible of some of the challenges, and this is one of them. The choice of using an APPT, as they don't use electric thruster for CubeSats, is because it's simpler, scalability down in comparison with other electric thrusters, and also because this is relatively easy to achieve throttleability, just varying the firing frequency and the electrode voltage, to provide a versatile device in terms of impulse drift. So as a quick reminder about the working principle, it is based on the impedance collapse between the two electrodes. Indeed, what we want is that the spacer, the propellant that is spacer between these two electrodes, is the most contributor to this plasma. So high currents develops, they concentrate and are spelled out the channel, passed by the Lorentz force that is a result of the interaction between the self-induced magnetic field and this current. Some configuration exists, but we have selected the parallel ray one for our studies. As an introduction of the experimental campaign, it's obvious that a comprehensive characterization of a discharge is a need in order to face the better understanding of the physics of this technology. And as intermediate step, it's necessary to work, or it's useful to work with breadboard models either in order to explore geometry and electrical variations. We account with a careful design and manufacture complete breadboard model, but finally we decided for this preliminary campaign to work with a very simplified version of it in order to isolate influence factor and so error sources. So now, firstly, I'm going to present the setup of these tests. Concerning the electronics, we are working with two analogous circuits. So one for the main, discharge, another for the triggering. I'm going to talk about the triggering later. And they are based on two states. The first one is to elevate the voltage from bus voltage up to kilovolts requirements. And after that, we need to charge the batteries that accumulate the energy for the discharge. We are working with a channel that is in the order of the centimeter, and both circuits are have different order of magnitudes. In the case of the main discharge, we are working with larger energies, obviously, and these are in the order of some joules. And for the spark plug case, we need a wider voltage range to perform testing. Also, we need to coordinate both the circuits, and the control was implemented on the spark plug circuit. And this is not maybe the best approach. Indeed, we want to implement in the next weeks another alternative that is an inductive circuit for the triggering. And this is the usual way to do it for spark plugs, ordinary spark plugs in the industry for other applications. We are going to, for our channel, we need to work under a pressure of the power of -5 millibars to ensure that we are having APPT discharges and no other kind of them. And concerning the probes, we have high voltage, high frequency bandwidth voltage probe, professional ones, because before we were working with in-house capacitive dividers, but we realized about the difficulties and the uncertainties. Also concerning the single Lamouille probes, we have placed them along the plume and separated from the center line and perpendicular, obviously, to the plasma jet. We also have to consider the circuit to bias them negatively, and also we have a fast camera, but not fast enough to run through the discharge. So we used in single mode, and also synchronization is not being an easy task considering the different delays, time delays. The triggering problem is to ignite in vacuum is not a trivial task if you don't have injection flow, as you probably know. Also, even more if we want the propellant to be the main contributor to the plasma. So it's true that the theory about flashovers along insulators subjected to vacuum and high voltage tells us that this path, the path along the surface of the propellant, is the weakest region to provoke a breakdown, but our order of magnitude are not enough, large enough in terms of electric fields to do it by themselves. So we need an external means to release some free charges that trigger a chain reaction with capability for that. We have tried many configurations with many materials, and finally we decided to use a kind of APPT, but smaller, that with this order of magnitude allows us to ignite around 1.5 kilovolts, but it shows high sensitivity to short variation due to erosion. Indeed, the filling, the electrode that fills the gap, it's also a key element in order to decrease the demands of voltage, but a weak point for accumulation of charring and metal vapor, what could lead to a short circuit that indeed we experience a lot of time. But we work with this configuration in order to ensure at least thousands of fires without problem. So this is a huge topic, but we are working on it in order to provide alternatives better and more reliable. So concerning the photography, we have reconstructed the representative discharge sequences, and we can see how the plasma evolved from the plasma sieve that comes from the spark plug discharge, and that goes towards the anode and increasing the intensity and expands along them up to its ejection. And the main conclusion of the analysis of many frames are based on that we have a non-uniform plasma distribution For example, we can see a kind of canting or at least inclination towards the anode so often, as it's many times referred on the literature. Also, we have perceived different regimes. For example, for smaller gaps, we have a more diffuse discharge in comparison to the nominal point that is the double of the gap, that where the plasma goes towards the electrode surfaces. And also we can ensure that we have plasma ejected, also validated by the Langmuir probes, and that the propellant is consumed, just not because the evidence that the plasma goes towards it, but also because with the surface analysis of the propellant surface, we see erosion. It's true that we have discharges without a Teflon bar, but this is more difficult to achieve, so it does not validate this conclusion. Also, we have some light points or hot points that we don't know if we can, it's early to say that they are the spots referring in the vacuum R literature, but also we have to be careful with some artifacts that are not the same and just could be reflection. Also, and that it seems to be loss of efficiency, we have seen that our plasma comes back along the anode's back. This is not something that we want, of course. Sorry. Concerning the surface analysis, we can see the surfaces before and after a characterizing cycle of findings. And we see the accumulation, for example, in the spark plug, accumulation of charge and metal vapor. And this is risky for the short circuit, to have a short circuit. And in the case of the main electrodes, for the smaller gaps, we have a more concentrated contamination in the center. And as we increase the gap, we have it towards the electrode, which corroborates the previous conclusion. Here we see the surface of the propellant, as we mentioned before, but it is still also early to set conclusion between the energy area ratio and the accumulation of charge. Here we see the perturbation of the vacuum chamber due to firings. We see that it is in the order of to the power of -5 millibars. Also, we can see how the turbo pumps work. Concerning the voltage measurements, we have here represented the nominal point for the main discharge and also for the triggering one. And we can see that repeatability is high, especially for the first cycle of the discharge, and also that we have two different, very different time scales. Indeed, the period of the main discharge is about 2 orders of magnitudes larger than the spark plug one. Also, we can say the perturbation of one discharge into the other in the both sense. Continuing, we have control about obviously the voltage of the main electrode, but not about the triggering voltage with this kind of circuits. Because of the difference of order of magnitudes of the time scales. Also, as we mentioned, there is a high sensitivity of it to erosion, to geometry variation, but it moves always between 1 and 3 kilovolts. It's true that we have trends, examples, that as expected, that if we decrease the gap or if we increase the electrode voltage, the triggering voltage will decrease because we are basically enhancing the local electric field. But we also have opposite trends, or at least no some conclusion trends as this one, this study that is the same battery, but with varying energy through the variation of the voltage, where we can see this kind of randomness. So concerning the time between the first, the spark plug and the breakdown point, we need time to allow the breakdown currents to develop. And this time is about 1 microseconds, but we can see dispersion in the data as we increase the gap, as we can see here for 2 different gaps. And we have also the reference of kind of the top reference of the thermal electron velocity, and this is not so so much inconsistent with our effective one taking these values. We also have different, for the more dispersed cases, we have different patterns, and we can see between another discharges, intermediate discharges that could be because of other non-desirable one. For example, the ones that we induce in the DC converters that we realize because they are also hearable as they are atmospheric. So we also, it's notorious that we have a kind of high frequency noise at the negative peaks of the main voltage discharge. It opens many questions, but this shares frequency with the triggering ones. So as this example, this is the triggering perturbation on the main line for the nominal point and for discharge main battery. It could be related as first approach with the secondary recognition that are widely also mentioned on the literature, but still unknowns, for example, regarding why we don't have them here. Finally, we can provide a fast estimation of the performance applying some electrical models. We can see that for this fitting, we expect about some kiloamperes for the largest current peak, and it provides us still a lower voltage of impulse bit, a lower impulse bit that was what we target, but it is still in the order of magnitude of the some of our references, as well as with the specific impulse. And finally, we are going to some very preliminary conclusions about the Landwehr probes test done. We have performed them in floating and negatively based versions. In the second case, because we want to perform time of flight and to collect the ion saturation current, saturated current. And we can see that at least we have two population of ions, and also that in terms of how to refine the test, that a larger bias favors the positive ion collection, decreasing this negative value. Concerning the results, they have been no successful because the maximum separation between the probes that we tested was about 10 centimeters, and the time delay was so small in order that we were incapable to decouple it from the answer timings. So finally, as next steps or some conclusions, this was a necessary first approach to the discharge basis, but also to the diagnostics selection and execution. What we need is to learn from this result, these procedures, and to try to focus on the open question list that we have. We have to improve the electronics and the diagnostics to continue doing the parameterization that we have already started. In terms of the test that we have shown, we also have to exploit the Landwehr test with the help of also direct current measurements that we also have started to read on. Our site, as in the nearby future, it's set on optical diagnostics because we find it as so useful in order to identify plasma composition, but it's going to be for sure a huge challenge. So finally, thank you a lot for listening to me. It will be a pleasure for me to try to answer your question if you have. So thank you.
Thank you. Thank you for a very nice talk. And so now we have time for question and discussion,
I don't
please.
know how to come back to. Sorry.
You hear me? You hear?
Yes, I don't know how to
Escape?
exit.
I mean.
Sorry.
What?
I think you just have to stop sharing your screen, Sherazade.
Yes.
Yeah, but I don't have it in Spanish or English.
Ah.
Okay, now.
Okay, done.
Okay.
Sorry.
Okay. So yes, please. Any question? Any comment?
There is a question from Tony.
I didn't.
Please, Marco, can you help me? I can listen to you anyway if you have questions in the meantime.
Tony, now you. Yes. You can talk, Tony?
Yes, I can, yes.
Okay, please.
Yeah, I mean, basically the question was that at the end you showed that you wanted to model the discharge with the snowblower model from Jan. I mean, the assumptions there underlying it are basically that you have a discharge arc that is traveling through a working gas, which is not typically applicable to an ablation-fed PPT where the discharge arc is rather stationary. So my question basically is like, what's your justification to use the snowblower model if you have a stationary ablation-fed arc rather than a traveling gas discharge?
Okay, because indeed you can have a sheet that is propagating down the channel. What we were studying about from the literature about how this chart could work is that even if we achieve to have a flashover along the surface, it all is mainly related about how the earliest stage of this chart develop in order to provide finally a kind of gas discharge along the desorbed gas from the propellant surface. So basically, once the discharge starts to develop intensely, you have a gas discharge. So you can compare this with electrical models as the nose flow model. It's true that it's so simplified and we are assuming a plasma sheet totally ionized and with and it will be no valid for sure for diffused discharges. But I think that it is still useful to provide us a rough order of magnitudes about our performance. In any case, we are conscious about the necessity of developing a numerical model that involves the plasma physics, and indeed this is the parallel work of our research, and we are working since some years ago on a plasma model. So
I mean, it's a challenging feat. I mean, you have all the plasma physics, especially with PTFE physics, is the polymer chemistry is challenging in itself, and you have a non-stable discharge, right? So you're changing your temperatures, you're changing your Knudsen numbers while you are discharging. So you basically have a very transient behavior that you need to model, all with overlying magnetic fields. So it's the modeling aspect is the rather challenging part there.
Yeah, it is indeed. As I told, we have been working with it for some years, not 2 years up to this moment. And yes, our goal is to provide a predicted code is very difficult, but at least a transient representative model for the performance.
Yeah, I mean, as long as you're aware, then it's good, because I just saw the slope flow and it was like,
yeah.
It's really not that good for this purpose. But if you, as long as you're aware that this is not a good model for it, then it's all fine with me.
Okay. So thank you so much for your question.
Yeah. Well, thank you for your presentation.
Thank you, Tony. So I think that now we can thank you, Sherazad. And now we can switch to the next speaker, which is Patrick Neumann from Neumann Space in Australia. And he will talk about pulsed cathodic arc thruster for CubeSats.
Thank you, Laurent. Just start up screen share, one moment. Here we go. Can you all see my screen?
Yes.
Fantastic. Thank you all for your time coming along today. My name is Patrick Neumann. I'll be talking about the development status of our low power pulsed cathodic arc thruster for CubeSats. to begin by outlining my talk. I will be giving a technical introduction to the physics behind the system before talking about the research history behind pulsed arcs and in general. I'll then talk about the development history at Neumann Space before moving on to our recent work, then current work, and then summarizing and taking questions. First of all, a technical introduction has already been covered to a large part by previous talks at this fine conference. But to reiterate, cathodic arcs are a source of dense, fast-moving metallic plasma. These sources have been used industrially for various applications for several decades. They produce cold ions, often with multiple charge states, sometimes as high as 5+, commonly measured in the lab. The electron temperature is moderate, 2 to 5 electron volts. The plasma is created at the surface of a conductive cathode. Unlike a PPT, we put the current through the cathode and evaporate, ionize it, and accelerate it using cathode spots to generate the plasma, eroding the surface of the cathode, forming a plasma jet, which is quite narrow, sinusoidal and sinusoidally distributed, normal to the local cathode surface. The quasi-neutral plasma forms and flows due to the discharge physics. There is a large amount of electrons inside the discharge volume, which form the bridge between cathode and anode, neutralizing the charge on the capacitor bank driving the arc. And this large amount of electrons can easily neutralize the plasma flow. This has been seen in the deposition community, and we have also demonstrated this experimentally as a propulsion system. These systems can operate in DC or pulsed mode. In a DC arc, the pulses can last several minutes. Pulsed mode tend to be few hundred microseconds, maybe up to a millisecond. They're both used in different deposition applications, which is where a lot of the research history is focused. They could be functional coatings, decorative coatings, a bit of both. And for a good discussion about this, I recommend Anders' classic text. There is less literature and application to propulsion due to the novelty of the field. I recommend having a look at Polk's work on modeling, Shine's work on aspects of ion and plasma flow, Kaidar's work on miniaturization for flight, Shashirin to talk about triggering techniques, my own previous work also on propellants. The vast majority of this previous work has been research. Current work for us is definitely focused on development, because when we apply these things in a technical fashion, dense drifting plasmas can be used for deposition and implantation applications. They are just as useful for propulsion for a number of reasons. That includes the broad range of propellants possible. Anything that is solid and conductive can be used as the cathode and thus the propellant in an arc thruster. Metals, alloys, semiconductors, this is most of the periodic table. They have many benefits because these materials tend to be dense, solid, more stable than quite a few other materials, do not need to be stored under pressure, can be easily transported. These are really useful when it comes to integration and transportation concerns. The narrow plasma jet produced by these systems, the plasma jet is often about 15 to 20, sometimes as broad as 25 degrees in semiconic angle, thus reducing plume interactions with spacecraft surfaces, giving greater freedom for spacecraft designers. The quasi-neutral plasma they produce does not require a neutralizer. This again simplifies integration procedures. You do not need the highly negative power rail to neutralize your plasma, nor do you need to strike a cathode neutralizer discharge or have a keeper. The pulsed operation of our system reduces power consumption because we can slowly trickle in power into the capacitor bank, charging it up until such time as we are ready to fire the arc. Additional power means more pulses per second. However, the impulse per pulse is not affected by pulse rate. Thus, for power-starved spacecraft, such as CubeSats, it is ideal as you do not sacrifice system performance when you are forced to be power constrained. Our development history has been guided by simulation. as we have been founded to develop and commercialize our systems. It was based on research work performed at the University of Sydney to take us from TRLs 1 through 3, utilizing plasma hardware in vacuum, but the PPU in atmosphere. That power processing unit is refrigerator sized. It's a very large, powerful system, but it is not designed for flight. It must shrink, it must be simplified. And we did our miniaturization and development, and a lot of our testing has been done in consultation with partners. For example, we received in 2019 a thrust balance from the Australian Department of Defence Science and Technology Group, which has assisted us mightily, helping us to move towards our TRL-4 CubeSat scale hardware in late 2019, and then to transition to operating environment through 2020, testing in constant consultation with partners. We utilized particle in-cell simulation to guide our progress to help constrain our parameter space. We have a TRL-5 CubeSat scale system operating currently, and we are currently testing our system to meet integration requirements for an upcoming flight opportunity. Our recent work has been redesigning for test and then testing for integration as we move from research and hardware to development hardware that can then go into flight. These integration requirements follow the functional requirements on spacecraft and spacecraft subsystems. These requirements can be environmental, such as NASA GEVs for vibration and shock. They can derive from system interactions, such as electromagnetic interference, exhaust quasi-neutrality requirements, heat generation and dissipation, measurement, and then iterative modeling. So, to talk about our recent work, we have been doing vibration tests, where our test philosophy is to test from the bottom up. We select what we consider to be our riskiest components, verify those assumptions with our test partners, then we begin partially populated boards, fully populated boards, then integrated units using local test partners. Some components that we use, such as these ones here, which are a type of capacitor, have been tested by their manufacturers only as far as automotive standards require. This does not mean they could not pass further tests, they just simply have not been tested to more exacting standards. Thus, their datasheet is silent as to whether they pass-fail for launch vibration loads. We conducted tests with a local partner on one of our chosen components. As you can see pictured here, these partially populated boards were populated to automotive standards, tested successfully, no loss in function, no change in charge or discharge, no change in total capacitance, and after X-ray, we found no damage to the solder joints. Further recent work has included initial electromagnetic interference tests. Because we are an electric propulsion system, we will generate electromagnetic signals. Whether these are of concern to our partners, this is something we need to work with them on. Again, philosophy is to test from the bottom up. Thus, we begin with testing our thruster head in isolation with simple sensors, then add complexity. This is part of a test we did with just the thruster head in isolation, looking for radiated magnetic emissions. We utilized a bare thruster head in vacuum with an external power processing unit to remove as much complexity from the system as possible and isolate potential sources of electromagnetic signal. We tested in our steel vacuum chamber with Hall effect sensors, fully aware that our chamber geometry limits our sensor choice, as we simply do not have the volume inside our chamber to implement a loop antenna. Additionally, the chamber material opposes artifact because it is a mildly magnetic steel. It is conductive, it will reflect electromagnetic noise. However, in consultation with our mission partners, these initial results have allayed their concerns significantly. They are now confident that we will not be an issue to their systems. As far as quasi-neutrality goes, again, we have done some tests on this and based our work on the quasi-neutrality established in the deposition literature. Although thrusters require a fundamentally different geometry, you must let the plasma expand to carry momentum away from the spacecraft. You cannot let it deposit onto a substrate. We have we test by measuring the current conducted to ground. This is the net current conducted to ground, and compare it to the currents supplied to the test hardware in vacuum. Here are a couple of plots with the supplied current versus the ground line current. That is the vector sum of supplied current showing the ions delivered into the plasma. We see from the ground line current that the discharge self-neutralizes. The net charge disparity is less than 1 part in 1,000, and the excess charge is electron dominated because this is an electron-rich plasma arc. This means that any excess charge can easily be rebalanced by drawing electrons from the space plasma. If you'd like more details on this one, I have a paper accepted on this for presentation at this year's IAC. Additional recent work has been our initial thermal tests, where we test from the bottom up again. It's not advancing, come on. We test the thruster unit in isolation and instrument with thermocouples, monitoring our system, monitoring our external power processing unit with infrared monitoring. We make reasonable assumptions regarding pulse frequency and the length of our burn in consultation with mission partners as what is a reasonable expectation to have for on-orbit ConOps. These initial tests that we have done validate our assumptions as to how much heat is being produced, where it is being produced, and where it is going. And it demonstrates that we operate within the limits set by integration partners. It also shows that no warm-up is required for this system. Cold start is inherent to this technology and thus more responsive on-orbit operations, as no time is needed to heat up cathode neutralizers or propellant tanks or prepare the system in any way beyond turn it on, tell it to start charging, tell it to start pulsing. Our current work is based around iterating what we have. Our steel vacuum chamber is suboptimal for a number of tests, especially electromagnetic interference. It is conductive, it is reflected, it is ferromagnetic. All of these interfere with electromagnetic tests. Our thruster requires vacuum to fire, and thus our solution is a polymer vacuum chamber placed inside an RF anechoic chamber inside a partner facility. The polymer is RF and magnetic field transparent so that we can use standard test equipment utilized throughout the industry, as well as the automotive industry for electronics testing. We can place a partner hardware outside the vacuum chamber, so we do not need the expense of vacuum-rated antennae. Our chamber has been delivered and commissioned, and we are awaiting test partner readiness for verification of our test program. Our current work also includes thruster development, where we are rapidly iterating through prototypes and accelerating our prototype iteration as we move through engineering qualification model production. We are building on lessons learned during our integration, and as our design evolves, so do our tests. For example, vibration tests leading to geometry changes, EMI tests as more partner hardware is delivered, and as our design evolves, we move towards TVAC and other testing to be done as an integrated whole as we move towards delivering our first flight model to our partners early next year. So to summarize, pulse cathodic arc thrusters have a number of benefits over other systems. They are simpler, they have solid propellant, they have dense propellant, they do not require a neutralizer, they operate with acceptable specific impulse, acceptable pulse ranges. They can do a lot of things for a lot of people. Neumann Space is driving their development here in Adelaide, South Australia, as we design for test, transition to flight, then test in flight to enable broader CubeSat and SmallSat capabilities globally. Thank you for your time and your attention. I will take questions from the audience.
Okay. Thank you, Patrick, for this very complete and dense talk. And so now the paper is open for discussion and question by the audience, please. Yes, Stefan, you want to start? Yeah. please.
Yeah, why not? Hi, Patrick.
Hi, Stefan. How are you doing?
Yeah, fine. Thank you. By the way, what time is it now in Australia?
Oh, geez. Add 7.5 hours to Paris.
Okay. Still feasible. I just have, I don't know, but I missed the performance of your system.
Yes. We are qualifying our current models as we speak, so I'm not really able to give you a good value. We have demonstrated a range of specific impulses with a range of different propellants in the past. We are currently using propellants that generate specific impulses comparable to full-scale Hall thrusters, so in the 1800 to 2000 range.
And in terms of input power?
In terms of input power, our system we are currently iterating for is a derated technology demonstration system for our first flight. It is rated to take 15 watt. Our main, and that's our derated power levels. We've been able to demonstrate as far low as 5 watts with much longer charging durations. And we have also had our, before we derated it, our system was working quite happily at 50 watt. The research apparatus I used previously would happily use kilowatts. So we know we can do the large power budgets. The challenge is, of course, with the miniaturization for CubeSats and small sats.
Okay, thanks a lot, Patrick.
No trouble.
There is one question from Jacek Kozina. Have you seen any difference between EMI signals in SS chamber and dielectric one?
Yeah, excellent question. We have not seen those yet. We're waiting on our test partner to signal their readiness for us to come and do tests with their standard hardware using our dielectric chamber. We are waiting on that commissioning so that we can do a direct compare and contrast with sensors inside the chamber.
There is other question from Christophe Capel. And what is the efficiency? And it is fixed or variable?
Ooh, another good question. Variable with propellant choice. With our current system, it can also be varied by changing the pulse parameters. We have demonstrated jet power efficiencies in some of my research work previous to this, quite a broad range, very low for bismuth, moderate for refractory metals, very high for certain light elements. As we are still qualifying the current model, I respectfully decline to answer that question as we are in the middle of our qualification campaign.
Okay, thank you.
And
I apologize, I cannot give you a better answer, but we're in the middle of the tests. Yeah.
No, the question was more on the fact that you have some efficiency, but do you master it? I mean, is it are you sure it will be always the same?
That is a good question, and I am certain we have not mastered the efficiency of this system. I'm certain there is good science to be done and excellent engineering to be done as well. After we demonstrate that the system fulfills mission requirements for these simpler models, then there will no doubt be the funding and the ability to further optimize the system for these small systems as well as larger spacecraft systems as we move along into the future. So I'm pretty sure we have not mastered this technology. It's simply due to its novelty. Unlike Hall and ion thrusters, which have had a few decades of very good, very focused research, a lot of the earliest I can find serious experimental work being done with vacuum arc thrusters is the late 90s, and those were only small little groups.
Thank you. Thank you. Bye-bye.
And maybe the last
Thank you for the
question,
question.
from Jacob Simons. Jacob, you can ask your question. Your microphone is
Sure,
on.
yeah. Thanks for the talk. It's very interesting. I was just wondering what the total delta V is for the upcoming flight, and if you could comment on any of that, the limits of that too.
Our upcoming flight, due to it being a technology demonstration mission and the requirements to fit on several other payloads in addition to us, we are not aligned with our thrust axis along the center of mass. So we will be demonstrating thruster performance by repeatedly spinning up the spacecraft and then having the magnetorquers despin the spacecraft. So in terms of delta V, it's not a particularly germane point.
Gotcha. Okay, thank you.
No trouble.
Okay, so I think that we can thank again Patrick for his presentation from Neumann Space, and I think now we have to move to the next speaker, but I did not see the next speaker. Stéphane, you see me in the list. So.
Sorry, Laurent. I said no. I'm checking in the list now.
No. No, I didn't see. No, he's not here, I think.
Okay.
Okay, so I think that, yes, so the next speaker, so we have a small break of 15 minutes, then the last speaker of the session is at 4. So we have a small break of 15 minutes. Thank you. So it's time to continue the session. And the last talk of that session is is given by Flavien Valency from Laplace Laboratory at the University of Toulouse. And he will talk about ion energy distribution measurement on a vacuum arc thruster with titanium cathode. Flavien, it's up to you, and you can share your screen, and you have 15 minutes plus 5 minutes of discussion.
Okay. Do you see my screen?
Yeah.
Okay. Okay, so pressing full screen. Okay.
Yeah. Yes.
So thank you. And hello everybody. So I'll present you our results on ion energy distribution measurements on a vacuum arc thruster. So after an introduction, I will present our experimental setup and then our results. So first, qualitative ion detection, and then quantitative results. So ion energy measurements and velocity calculation. So here we study vacuum arc thrusters. So in this kind of thruster, the propellant fuel is the cathode. So we get first from ejection of ablative material from cathode. So the specificity is that we use a solid fuel. Is there not? So we don't have issue with valves and the mechanical parts. We have no mobile parts, and then we have a compact design down to 1 U. So generally the main discharge is triggered by high voltage, and the thruster operates in pulse operation at a various frequency, and this can achieve a various range of missions from orbit raising to deorbitation. So the thrust is low. It's a range of millinewton or less. So, but we can have a high specific impulse. So here in the small schematics, you can see that the disposition of the thruster, and then the trigger creates the main arc and ejection of ions. So we got multi-charge ions with high velocity. So since ions the ejection of ions is related to specific impulse and thrust, it's important to consider these parameters, since the ejection can reach a few tens of kilometers per second. So the highest values in the literature can be reported to close to 100 kilometers per second. And the specificity is the production of multi-charge ions. So in order to improve the device, it's important to study the ion charge and energy. Now, this project is conducted in the frame of ASH 2020 European funding, and with led by COMAT. So you saw the presentation yesterday. So the model, the thruster we study here at Laplace in Toulouse is a PGP 30 watt thruster with a 0.45 millinewton thrust. The total impulse is about 4 kilonewtons per second. Specific impulse of 2000 seconds, and this fits in a 1 U volume. And the propellant, so the titanium cathode, mass is 160 grams. So you see an image of the thruster in operation, and an idea of the current waveform. So a pulse duration about 20 microseconds, and the current of a few kiloamperes, and a voltage, so 250 volts. So it's used stored using capacitors. So here is our experimental setup. So we have a chamber, to the 200 liter chamber. We can come down to a secondary vacuum down to 10⁻⁶ millibar. So the voltage U of 16 volts is the power supply to the unit. So there is a voltage increase to charge the capacitor to 250 volts inserted in the electronics of the thrusters. So here we perform mass spectrometry. So we present results from mass spectrometry. We use a HAL EQP 1000 mass spectrometer from a hydrogen energy core. So we can have a 100 micrometer collection entrance, and the thruster is positioned 10 to 15 centimeters away from the mass spectrometer entrance. And we integrate over all the discharge and the post discharge during 6 milliseconds to catch all ions. And we can we sweep energy from 0 to 100 eV. So the interest of this approach is to get an energy distribution for each level, for each ionization level, and get also a mean analysis of the ejected mass analysis for the ejected particles. So of course, the project includes other laboratories that focus on other parts of the process. So here are first results. The first study was a scan as a function of mass. So we performed a mass spectrum of the plum to scan the several ions sorted by mass. So the mass ratio M over Z. So I recall the parameters. So of course we can see a strong peak at mass 48, corresponding to T plus titanium ion and its isotope. So on the left and the right, we can see small peaks corresponding to titanium isotopes. And we can have also detect ion up to T8 plus. And this was not for all the tests, but we can see even up to 10 plus. And so we've done a mass charge estimation yielding to 2.5 to 3. So it means that the average mass corresponds to T3 plus. Of course, this corresponds to the scan range from 0 to 100 eV. So now we've done energy for which shows one specific ion. So in this case, it's T plus, and we scan from 0 to 100 eV. So what appears is a first strong population centered around 20 eV, but we also see the beginning of a higher energy population around 80 to 90 eV. So now we scan the other ions. It seems that when we move toward a higher charge level, the second populations move for higher energy. So we can clearly see it for T plus. We see the beginning of it for T2 plus, but for T4 plus, and in particular for T8 plus, we can only see the first population. So the strong population is so between 20 and 30 eV up to T4 plus, and we can only see the second population for T2 plus and T2 plus because we're limited to 200 eV, and this indicates that it's likely that there are higher energy population, especially for higher charge level, perhaps to 300 of eV. So now we try to convert this data into velocity of ions. So we made the hypothesis that the measured energy corresponds to the kinetic energy. So we neglect the potential energy of ions, and we calculate the velocity according to this relation. And so we see the same graph as previously, but the scale is in kilometer per second instead of electron volt. And so this yields to a mean velocity between 13 and 14 kilometer per second. And if we look for higher charge level, so we still see an average velocity between 13 and 15 kilometer per second. And for T plus, 8 plus, sorry, we only see the first peak. So of course, this indicates a lower velocity between 5 and 7 kilometers per second, because this corresponds to the first peak we see also clearly in the case of T2 plus and T4 plus. So it is likely that for high charge level, we've got the population moves for higher energy. And of course, this velocity of 5 and 7 kilometers will only correspond to the first population, and it's likely that there is a higher energy population, so that the velocity associated to T8 plus should be largely higher than 20 kilometers per second. So to sum up these results, so we have some limitations for the detection. So first, the reproducibility. So we've got issue to get a highly reproducible working process. So it's good to remote measurement. We're able to detect up to T10 plus, but with higher uncertainties, it was not possible for. We cannot see that for all tests. But results are really good up to T6 plus. So the main limitation is that our mass spectrometer is limited to 100 eV, and if we see the results that, if we remember yesterday during the presentation of COMAT, so speed up to 40 kilometers per second were reported. So this is likely to be associated with higher energy population. So if we extrapolate the comparison between energy and velocity, that would mean about 150, but to about at least 200 electron volts. So there is still some work to do for using mass spectrometry. So here I presented a few the scan of a few ions. So we can try to do the measurement from T plus to T10 plus for the 10 ionization levels. This will help us to have a better estimation of the ion mean charge. And another interesting study will be to check the distribution of ion as a function of time. So here results were integrated all over the pulse and post-discharge to catch all ions. But it will be interesting to scan as a function of time during the first microsecond, the second microsecond, up to 5, 10 microseconds all around during the pulse to see how the population of ions are emitted during time. Because we suspect that the first high energy population is ejecting during the very early stage of the discharge in the first microsecond, and then lower energy ions are ejected after this step. So this study should also be completed by optical emission measurements. So we developed optical emission spectroscopy targeting VUV radiation emitted by high charge level ions. So we plan to do the detection of this ion through spectroscopy, and also use spectroscopy to perform diagnostic of the plasma for using to get temperature and electron density. Okay, so thank you for your attention.
Okay. Thank you, Flavien, for your very interesting talk about measurement in the context of vacuum arc cluster. So now the paper is open for question and discussion. In the audience, please, you can ask your question and make your comment. Okay, Stéphane, you can start, and then Christophe can continue.
Thanks, Laurent. Hi, Fabien. I have a quick, very quick question. I was wondering. So first, pretty congratulations for those measurements.
Thank you.
That would be very interesting. That are very interesting and will be very useful for us and for everybody participating into this project and for the development of the PGP. But is it roughly what we expected in terms of charges and ion energy at this power level?
Well, in literature, it was reported at least 10 plus. So if I recall correctly, there were reports of even higher charge level. So yes, we did expect high charge level. So we were able to detect about up to 10 plus. But the problem we have is that with the low reproducibility, we cannot catch at all tests the 10 plus. It's reliable up to 6 plus. So it's possible that we got even higher charge level than 10 plus, perhaps 15 or 15 plus.
Thank you, Stefan. Christophe, you want to ask a question?
Yes, thank you for your presentation. I was looking at your scan with the mass spectrometer. A basic question. Are you sure all the titanium has been ionized? What is a part of titanium non-ionized? Zero?
Neutral. So
neutral.
Yes. So there is the possibility that we have neutral titanium, of course, but we expect that there is a quite strong ionization. So the detection we use, we have two modes of the mass spectrometer. We can ionize a particle that goes inside the detector and then use measurement on this. Or here we use a passive mode, so it's set to only detect already charged ions. So in the measurement equipment, we didn't search for neutral ions. So of course, there is a possibility. It will be interesting to do some kind of global balance of all charge level, including zero level.
Okay, that would be very interesting to get that value. Thank you.
Thank you, Christophe. Other question, other comment? Okay, I have.
Vas-y, Laurent.
No,
sorry, Laurent.
Patrick. Patrick.
Thank you, Laurent, and thank you for your presentation, sir. More of a comment to help answer some of the other questions coming through from the other members of the conference. The ionization fraction for materials like titanium tends to be 90% or greater. So the vast majority of the material is ionized and can be ionized to quite high states. There are a couple of papers by Yushkov and Anders where they look at some transition metals like platinum, and they have quite a substantial population of 10 plus ions. In fact, some of their work shows the majority, that the most populous charge state to be 7 plus for a 4 kiloampere short duration arc. And some of their other work looks at the average kinetic energies of the ions as well. For titanium, they report a value for about 150 ampere arcs after 100 microseconds into the pulse of approximately 122 electron volts. So there are interesting things happening inside the cathode spot, creating very high charge states and then giving those charge states quite a lot of kinetic energy. Thank you again for that wonderful topic. I would also love to see more work done with a mass spectrometer with a higher energy range. I think that would be fascinating.
Thank you, Patrick, for your comment. Yes, I have myself a quick question for you, Flavien. You were talking at the end about optical emission spectroscopy measurement, but are you able? I mean, do you find all the data from that measurement? You are able just to determine through the line to determine the population of ions. Is it not difficult to find the data for that, to do this transition?
Yes, the fact is that the spectrum is quite heavily charged. We have a lot of lines. So ideally, we can see one line. Okay, this line corresponds to T plus, this line to T2 plus, this line to 3 plus. But the fact is that we have a very large mixture of lines. So we try to search in database to search if there's a spectral area in which we can say, okay, if we have a maximum intensity, this corresponds specifically to, for example, T2 plus or 3 plus. So we are ready to search, but it won't be easy.
Yeah, okay, I think so. Okay, so if there is no more question, we thank again Flavien for his very interesting presentation. So now we have a break, and we will start again at 5, and we will do a roundtable. And the topic is small plasma thrusters, challenges in numerical simulation and experimental validation. Okay, so we come back at 5. Now we have a break. Okay, thank you to all the speakers of the beginning of the afternoon. Thank you to all of them.
Laurent,
oui.
C'est toi qui as la main à 5 heures.
Je vais la garder, ouais, parce que je vois que tu devais partir un peu plus tôt, c'est ça. Mais je vais la donner à. Enfin,
je vais la donner à Francesco.
Oui, bien sûr. Je pense que. Mais tu as eu des nouvelles alors de Francesco?
Je sais pas, il m'a écrit, donc il est là.
Ouais. Non, parce que je sais pas comment il va organiser ça. Bon.
On verra nos
non, mais je pense qu'il a pris. Je sais pas. J'avoue que là, on lui a laissé carte blanche un peu et. Une carte noire, je sais pas.
Non, ça va marcher.
Ouais, parce que c'est vrai que moi, j'ai pas trop réfléchi non plus. Enfin, j'ai quelques. Voilà, bon, on va lancer des billes, mais je pense que. On va voir quoi. J'avoue que j'ai pas plus que ça. Ah, Francesco est là. Attends, je lui passe. Ok, je vais passer Francesco. Je vais passer dans les panélistes.
Ouais.
Ok. Hi, Francesco.
Okay.
Okay, now we can talk.
Yes. Yeah, I was exactly asking you on the chat how.
Sorry.
Yes, but okay. I mean, I just raised the hand. So practically, yes, I need also to share. I prepared just.
Yeah. You can do it. You can share now the screen. You are in the panelist, or you are in the list of writers.
Right. Just. Let me see if you can.
Yes, we see your screen at least. Yeah.
Yes, but now I can go to the presentation and you can see. I want just to show the title of the roundtable.
Yeah.
Showing the component of the panel.
Yeah.
Even if I received an email by Wono.
Yeah, okay, because due to the jet lag, no, I think. I mean, due to the time, he's not here. Yes.
Yeah, he said that. It's very probable he will not join us because it's very late in Korea.
For sure. We were talking about that with Stefan before.
It's okay. He's a half hour earlier than me. I'm fine. No worries. Just
great.
He's lazy.
Look, I parked my bicycle down here at the office because I figured driving my car home would be a foolish choice this late at night. I'll stick around for the roundtable. Have a good chat with you all. No worries.
Okay.
So
thank you, Paddy. So
great.
I will keep this slide because to give the possibility to the audience, just in case they want to ask some question in particular to one of you.
Yeah.
And I want just to show how I'm thinking to divide if you agree, the roundtable, since I want to let's say mainly manage 3 different discussion with 15 minutes for every discussion. One is about let's say general scientific line of investigation for the different configuration. I see that in the panel we have expert in not for all the spectrum, but mostly many of microthruster are covered. So which kind of physics we need to understand better, and if there are possibility for or room for improving our understanding. And then I'd like to move to the challenges in the experimental diagnostics, since we know, I mean, these are very small devices, so probably the problem of invasive diagnostic can be serious. And then Laurent, mostly me and you, we can contribute on the challenges on numerical simulation of microtrusters. Since well, probably it's better for us because small trusters probably are better to be simulated, but I think that we can contribute more on defining possible challenges or future development for numerical simulation. I think that probably at the end we will cover the 1 hour.
Yes, for sure.
Extension,
yes.
Because
okay.
I mean,
so
just 15 minutes.
Yeah, so I tried to.
Francesco, in the first title, line.
Yeah, tell me. Yes.
Stefan,
go ahead.
No, Stefan has some problem with
connection. Okay.
Stefan, we don't hear you.
Oui, c'est bon. I'm back. You missed the O in performances.
Performances, yes. Okay, and I send a message to Yevgeny but I think yes, to accept to pass in the panelist in the other panel.
Yes,
because
yes.
Michael is there.
Let me. No, I did not see him. So Michael is not.
Francesco, did Michael answer your email? He will join.
Yes. He said that
so
we'll join.
No, okay, no, yes, we have alpha. Yes, we have alpha now.
Yes.
Yeah, we will still are ahead of schedule.
Yeah, all say yes, apart one no.
Okay, we wish he okay.
Just Laurent, how I can see possible people rising the end?
So I will give you. You will be the. You will be the chairman. Let's say. Okay.
Yeah, but I have to stop the sharing the presentation. Otherwise, I cannot see the question from the chat. When you
No, I think you see it.
No. When I share the screen, I see the presentation. I don't see the let's say the screen of Zoom.
I don't know. Yes, I don't know.
Yeah, showing you the pictures and showing also possible people raising the hands or chatting. I don't see this when I'm sharing the presentation.
So what you can do is that Laurent could share his screen.
Laurent can, okay, we can do this. I can share the presentation and
Laurent check the hands.
And yes. Laurent check the hands and give the yes.
Okay.
Yeah.
So I can. So I will stay. I will stay as an animator. Okay.
Yeah, but okay. Please, Laurent, just when we finish the round table, I don't want to. I mean, I want first you answer the questions, and then after the first round, for every line, we can leave the floor to the audience. Then we move to the second line, and then to the third line.
What do you mean? I mean,
line. I mean, these 3 lines I want to discuss.
Okay.
You should ask if there are any comment from the audience.
Oh yeah, for sure. But I think
if not, they will never participate.
Yeah. Okay. I agree. Okay, but we arrange things.
Yeah, but probably let's see. But probably 2, maximum 3 questions from audience. Otherwise, probably we don't have time. But okay, we check. I mean. Depends.
I'm not sure because I mean I want that the audience at the end participates more than me. I would say in the discussion. I would say that it will be because
usually it's the opposite. You will.
Okay, we see.
Yes.
If I know Yevgeny, start talking, probably will take 1 hour.
We never stop.
And
okay. Why not? Okay,
I'm joking. Just Stefan, let me know. Do you want you be the first, right? Because then you can leave.
Because I have to leave around 20. Because
Okay. For this reason, do you want I can manage first the challenges in experimental diagnostics.
Yes, maybe.
Probably you can contribute more on that.
Yes, you're right. Maybe, no?
The
Yeah.
No,
I
we
think
can't.
that your ordering was correct. And I think it was great to start with what you proposed first, which was broader and more general, and then to focus more on diagnostics and then simulation. But yeah, we can change the order if you want. Or
well, no, I mean, you also, due to your expertise in general new concept on electric propulsion,
Yes.
you have also a wide idea on line of. I mean, anyway, you will be the first. Let's say.
Okay,
then,
I do my best.
I did not think. I mean, yeah.
Yeah. Okay. We then we can include as much as possible the audience.
Yeah,
but,
for sure.
Let me. I mean, Laurent, just help me because you can check from the audience if we have.
I
will ask you if we have questions or comments from the audience.
Okay. Good.
And then, if not, we can move to the other line.
Yes. But okay. See you with. Okay, donc, so Yevgenia, but Yevgenia has to accept to change of list. He did not yet. But then who were in the list? Who was in the list? Michael also. Okay.
Yeah, I can. Okay, I showed.
Yeah, I didn't see him.
I shared the screen again.
Okay, don't use. Okay.
You can see the list.
So now you say that you cannot see the. Okay.
Now no.
Okay.
Now I'm again in presentation mode.
And Igal is not here also.
But he said that will join.
Okay. So yes, we have.
Every one of you send me an email confirming the.
Yeah, I will do it. I'm doing it.
I don't know if it's better like that, but I mean, guys, it's.
So how is it going?
Well, after almost 2 years of COVID, still alive.
That's already a good point.
Oh yeah, it's 2 years, but seems 20.
Yeah.
No, this was a awful time. Everybody.
No, it's a pity because I really was in favor of on-site conference because you know, I mean, it's much better and but
impossible almost.
No,
difficult, very difficult. Yeah.
But
you know, the first we have done some tests, you know, for people to check the presentation. And the first day, and Igal were discussing with us during maybe half an hour because he need to talk. You remember Stefan? And need to talk.
Yeah, he wanted to talk to somebody.
Yeah, that was crazy. We wait.
He told us, I have to talk.
I never talked too much. I mean, so much time with him. Never. And he was talking about this problem.
But he told us that basically he had no interaction for almost 2 years.
Yeah.
His family.
Yeah.
With no one.
Yeah, it's very difficult, and also with student, he has a big problem, and it was very difficult for him. And he want now to have his own company, so he want to leave Technion.
Yeah, I saw. Yeah.
Okay, you saw.
And, I saw that he moved from Technion to have his own company.
Yeah,
and,
but I think it's partly due to the COVID situation. I think.
Yeah, this is the feeling I have after talking with him. He was a bit sad, and also he was
a bit depressed. I mean, it was a bit that was. I think it was terrible for him. He was, I mean, talking a lot of that with us, and
yeah, and also, I mean, in Israel, the situation is never normal, and he suffered a lot from the political situation in Israel. In fact, different time he said that he want to move back to Europe, and try to yes, he want to go back. He was in Europe.
Yeah, he was in Germany. Where he was? He was
Germany.
In Germany. Yes, I remember.
Yes, for his PhD.
Yeah, okay.
And after living in Europe, in fact, I mean, he was really happy. But the problem is that it's very difficult to find position available, and he's very good and talented guy.
Yeah, but the competition is very
competition, right? So and well, I mean, hopefully in the summer situation is better, so we have the possibility to have, let's say, normal summer to recover a little bit. But then during the winter, at least last winter in Italy, the wave was the COVID wave was quite serious.
Yeah, because I remember at the beginning, the south of Italy was a bit, far from the
exactly
from the
first wave, but the second wave was terrible, and they took a strict decision, like closing the school, like I mean, and all these duty go to the family. So, and was really
I know.
yeah, I mean, yes, to have a kid in this time is really difficult. And now you see, I mean, this wave was much weaker, but because probably was the effect of vaccination.
Yeah.
So let's see. I mean, probably we need one more vaccination before to really go to the end.
Yeah, but if but we have to wait. I mean,
the problem is that is a pandemic. If you don't vaccinate all the entire world, where you will receive always mutations, variations.
Variants.
Variants. And your vaccine is no more effective.
Yeah, you're right. Totally.
So it will continue forever.
Yeah, that's the point.
Speaking as someone who's starting to come out of winter now and looking forward to spring,
that's true.
Yeah, I think I'm actually the only person presenting from the Southern Hemisphere. The Singaporeans are 1 degree north of the equator.
Okay.
Yeah.
So you are.
Australia, we currently have our 2 largest cities under varying degrees of lockdown, and in comparison to a lot of other places, those waves are not bad in terms of total case numbers. Sydney, a city of 5.5 million people, has for the last week or so been having about 1,500 cases a day, but they're all Delta cases, and with fairly intense lockdown conditions in Melbourne and Sydney. The fact that it's still being able to spread with an effective R value of about 1.2, 1.25 has been helping to drive vaccination rates in this fine nation of mine. I look forward to getting my second AstraZeneca shot in about 20 days. So that's going to be good. But yeah, even with fairly intense lockdown and modest vaccination rate, Delta can still grumble along in the background because of the people who have to work so that people can shop from home, people can do deliveries for those people. It's not the birds that carry the milk off the supermarket shelves to your doorstep. So yeah, it's getting as many people vaccinated as quickly as possible is important, and I'm loving the news reports I'm hearing about more nations agreeing to waive the intellectual property requirements for to permit low and middle income nations to make generic versions of the vaccines. so that more people can be vaccinated more rapidly.
That's the only way, because they cannot afford it. So if we want to solve the problem, we have to vaccinate everybody, everywhere.
Yep.
So generic is the clue.
Yep.
So guys, I think I will have a real break. So a coffee.
Okay, so we will
We'll join again in 15 minutes.
Yeah,
So we start at 5. We will meet in advance.
Okay, okay, perfect. See you soon.
Laurent, just a quick question. He left. Okay, I will ask him later. Okay, yeah. I see you in 15 minutes.
Igal is joining us.
Ok. Laurent?
Ouais.
Juste une petite question, parce que je ne me rappelle plus. C'est demain matin, c'est moi qui commence?
Oui.
Ok.
9h20, c'est.
Ouais,
en principe, je serai là, mais comme j'ai mon testing.
Non, mais ok, mais pas de problème. 9h20, c'est pas. Ça
bon, sinon, si ça me fait chier, je vais me voir leur truc. Hein, parce que
non, mais pas de problème.
Ils vont nous expliquer comment appuyer sur une souris.
Ouais, bon, on ne sait jamais.
Non, ce que j'ai peur, c'est que des fois, ils font ça et puis après, ils te lancent, tu sais, la vidéo qui. C'est le truc. Bon, allez, on fait un petit break. Allez,
ça marche, à tout de suite.
Eagle is here. So,
Hey, Francesco.
Hi, Gal. How are you?
Fine. I don't know if I'm allowed to open the camera.
yes, you can do.
Yeah, sure.
You can do.
Okay, nice to see you.
Yes,
So congratulations for this new
yeah.
adventure.
Adventure, exactly. Exactly.
I'm very happy. I'm very happy for you.
Yeah, I hope.
Yeah. Let's hope. I mean, you deserve a lot, because I mean, if you have the possibility to really show your idea, and as a company, I think that is. I mean, you can be much more proud of you.
Yeah, I think at this juncture, yeah, academia is a bit of a problem for me.
Yeah, I see.
Yeah.
I remember last time you talked with me about the problem of staying and keep the position there.
Right.
Yeah.
Well, that's life, you know.
Well, yeah, is anyway, it's hard time almost in all the countries. I mean, in Europe.
Yeah, the pandemic also, you know, it's restricting travel. It's really hard.
Make everything, yes, more complicated.
Yeah, there was a message. I think there was a message there from Evgeny.
Yeah.
Oh.
Okay, I see Evgeny.
Yes, he's here. Okay, now he's here.
And now I see Evgeny moving.
Yeah. Now.
I'm listening starting from 5 a.m. Come on, guys. How did you ignore? How did you ignore?
I'm currently listening at 12:30 a.m.
5. Start at 5. Yes.
Hi, everyone.
Hi. So everybody is here. How many people?
Yes, from the let's say from the panel.
Yes.
We are all, since I've said before, 1-0 sent me an email and yes, it's very late in Korea, but I mean, it's very late for him.
Paddy is a bit younger, I think,
yeah.
So that's why he can survive.
Okay.
It's just like a real conference, man. You listen to all kinds of fascinating things during the day, and you wind up having conversations till just after midnight. Yes. You know, it's just like I'm there in person, you know?
Yeah, we just missed the beer.
That's the point.
Yeah, look, yeah.
It's up to you, Stefan. I mean, if you want, we can.
I could use delivery or Uber, maybe Uber beer. Yeah, it does.
Uber beer.
Well, yeah, we missed that part, right?
Well, I have my pickup. Okay. Okay. So just, I mean, Laurent, tell me when we can start, and then I can introduce you, and we can start the discussion.
Yeah, I think that we can ask the discussion. Yeah, the panel is the roundtable. Okay. The panel is open. Yeah. Okay. So good afternoon, everyone. So this is the first roundtable. So I'm sharing the screen so you can see some slides I prepared for you. And so please let me know if you see the slide. Yes.
Yes, okay, perfect. So this is the first roundtable. So we have a second one tomorrow, if I'm not wrong, at 4, right? Is tomorrow. And but tomorrow the roundtable is more devoted on the technological aspect of the small plasma thruster topics. So today we are mostly discussing about the scientific aspect, and we can discuss about the different challenges and possible room still available for better understanding the physics involved, in particular to small plasma thrusters. So on the scaling down on the plasma thruster for the different configurations. And so I'd like to introduce first the component of the panel. And so it's a real pleasure to have with us Evgeny Raitsets from Princeton Plasma Physics Laboratory. So he's the leader of the plasma thruster laboratory at PPPL, and in particular is expert in all thruster physics and also possible new configuration of all thruster based configuration, and in particular also is working on air briefing concept. So we have I hope so, Michael Kedar. I don't see him, but probably will join us. Michael is professor at the Department of Mechanical and Aerospace Engineering of the GW University. Then we have Patrick Neumann. Paddy is the chief scientist of the Neumann Space in Adelaide, Australia, and is mostly working on the pulse cathode arc thruster. We have also Igal Kronhaus with his new company, Space Plasmatics, and he's working mostly on electric propulsion technology that he developed in the last year at the Aerospace Plasma Laboratory at the Technion University in Israel. And is expert in vacuum arc thruster and all thruster. Then we have Laurent Garrigue. Laurent is research director at CNRS and at Laplace Laboratory, and is expert in numerical simulation, fluid, hybrid, and particle in cell simulation of mostly all thruster configuration. Then finally we have Stéphane Mazoufre. Stéphane also is research director at CNRS and at the ICAR laboratory, and he is also head of the Oracle Joint Laboratory with ExoTrail. And he's expert in all thruster, but also in new electric propulsion concept, in particular studied by laser-aided diagnostics. So I was thinking to discuss and to follow this round table on 3 different important lines. First of all, I'd like to discuss with the panels about possible new or possible scientific aspect that we need to understand better in order to improve the different micro thruster configurations. Then we will move on the possible challenges in the experimental diagnostic on micro thrusters. And finally, we see with expert on numerical simulation which kind of challenges we have on the simulation side, on the numerical simulation side of the micro thrusters. So concerning the first point, so I think that we can take 15 minutes on the different point. So concerning first point, I'd like to have the opinion of the panel, but I hope also to have contribution from the audience about the possible physical effect of phenomena which we think to be improved, to be understood better in order to improve the performance of micro thrusters. So generally speaking, we deal with plasma. So we need to ionize and accelerate plasma. So the mechanism that we want to really understand better is how to increase the ionization efficiency and acceleration efficiency of plasma in such a small devices. So we have to take into account that plasma means also is strictly coupled with the electromagnetic configuration. So we cannot separate plasma with the electromagnetic configuration we want to understand, we want to use. And but due to the small scale, we have to think that it's not just question of source of plasma and coupling with the external power, but is a question also of losses. So what we also need to understand better is how to avoid the losses, since in such a small scale devices, the interaction with the wall or the surface to volume ratio of our toy, of our guy is very important. So this means that we should think about the electromagnetic configuration also from the losses part of the balance equation. And as this regard, in my opinion, the surface and the material of the surface becomes very important, a very important ingredient for the micro thrusters. So I'd like to know what are your opinion and what is the most important physical aspect we need to understand. So I will start with Stefan. So please, Stefan.
Thanks, Francesco, for giving me opportunity to give my viewpoint on that topic. And you said a lot. You said a lot of things, very important things already. And I fully agree with what you have said. I think it should really be clear for the audience, and maybe especially for the young people joining our community, that if we want to accelerate the development of thrusters, if we want to improve the performance, if we want to build and develop new concepts, we indeed have to better understand the physics involved in those miniature sources. As you mentioned, since we downsize, so we have small sizes, so dimension, surfaces start to play a very important role. And I fully agree with you that probably we should better take into account the interaction between the plasma and the surface for all the type of mechanisms that we want to involve. But I also would like to say that what makes probably things difficult for all of us is that we have a very large variety of concepts with probably very different physical mechanisms at play. So this makes life a bit more complicated. It's probably true for simulation, modeling, and also for diagnostics. So probably, I mean, if you compare a vacuum arc thruster with a gridded ion engine, certainly that the physics behind the plasma creation, ionization, confinement, acceleration, and generation of thrust are very different. So also they rely on the same equation and the same physics at the very low level. But in our case, compared to very large thruster, certainly in addition to mechanisms like ionization or confinement, as you mentioned, and the effect of the magnetic field, we should certainly also consider plasma surface interaction. That means that, as you said, the material and the entire wall property or surface property becomes also very, very important. So
yeah, we lost you, Stefan.
We lost Stefan.
As always, the most interesting part gets cut out, right?
It makes life even more complicated because we can probably separate the more complicated at a small scale.
Yeah, Stefan, sorry, could you repeat
the end?
Last minute?
No, I don't remember what I said. Like a red.
Hey, we will discuss about the plasma wall interaction.
I just want to emphasize on the fact that it's probably even more complicated to better to understand the physics at small scale, because we have to account in addition for the role of the surface. And we cannot separate the plasma discharge and the surface.
Yeah. In fact, I mean, in this regard, probably we should think about, to having a possible active surface, like there are experts also in material processing and plasma wall interaction that use the wall, in fact, as an active element and not just a loss element. And but probably we can benefit of Yevgeny Raitsets from for this discussion. So please, Yevgeny, give your contribution on this aspect.
Thank you, Francesca. And basically, I second all of you, both of you, on all aspects of issues and challenges which you just mentioned. But before I say about materials and plasma wall interaction, I wanted to comment maybe the same line which Stefan said, but when we're scaling, let's say we're taking conventional thruster, which we know very well, let's say arc-jet, whole thruster or something like that, and we're scaling it down. We basically, on a normal medium scale or large scale thruster, we know almost everything, right? I mean, we can simulate even almost everything except like the most important part, transport. But it will come when we will have three-dimensional codes, right? Or something like that. But when we're scaling it down, things which were important for large thrusters become to be less important for small thrusters, but things which were less important for large thrusters become to be more important. For example, I just give you an example which is close to my heart is the whole thruster. Processes which happens in a channel, always important. But when you're scaling it down, processes which happening at the center of the thruster become to be crucial. It doesn't matter which one you take in, annular thruster or cylindrical thruster or wall-less thruster, doesn't matter. Central processes become to be important. in making actually us connected closer to the magnetic nozzle thrusters. So basically things which we never addressed in details because community was not so much focused on micro thrusters concepts. Now, regarding materials, actually, Francesca, it's a very good idea. I didn't think about this, to make whole thruster with self-healing walls. It could be, it could be worthy direction to go. Honestly, I didn't think about this, but now, thanks to you, I start to think about this, how to make it.
No, I mean, I was thinking also, since, I mean, you are expert also in air breathing application. And as soon as you have alternative propellant, the interaction with the wall becomes more complex than with simple noble gases. And we know that the chemistry of the surface is a really active chemistry. And in a small thruster, like in micro thrusters, this surface chemistry can even drive the global performance of the thruster itself. So, and yeah, please.
Totally agree with you. Chemistry, even probably, for catheters as well, even for, even if you're not air breathing, but most of these applications seems to be targeting low Earth orbits, right? And so presence of residual atmosphere, whatever it is, for small thrusters can be also kind of impose devastating effect on operation of the device. And air breathing is for sure. And in this regard, we may learn or may kind of have a more synergy with plasma processing community, which deals with this type of plasmas for a long time. And so probably we will need to learn from them or to engage them in this, research. I know that many of you have collaborators or like organizations which have both branches, thrust propulsion and plasma processing. But I think it's a very important point which we need to learn and to introduce it in our thinking. And as we introduce chemistry in modeling, it will become even more complicated, right? I mean, because it's still low pressure. So it's not clear if global models will be kind of sufficiently good for such applications like we're talking about. And so, yes, it's a great challenges. So
just an example, there are already some numerical evidences that by changing the propellant, and so the chemistry of the thruster, the chemistry involved, you need to change completely the geometry of the thruster itself, since the chemistry really has such a big impact that requires some time to change geometry or magnetic topology itself. And unfortunately, it seems that just changing the propellant by keeping the same thruster cannot be a good idea. So I'd like to also have a contribution from IGAL, Kronhaus, and that also can contribute on this discussion still on all thruster, also on the vacuum arc thruster. And after IGAL, I want to know the opinion of Patrick Neumann, which is expert on also on the cathode arc thruster. So please, IGAL.
Yeah, thank you, Francesco, and everybody on the panel here for inviting me. I was busy in the last 6-7 years trying to develop new concepts of microthrusters, or improving existing concepts as well. And indeed, the difficulties are astonishing. when you deviate from conventional designs, you encounter things that just don't work, and there are a lot of difficulties of well, the physics are not, even if like Evgeny said, transport is still not fully understood in conventional Hall thruster for 50 years. So in these new devices, it's totally new. But it also allows you flexibility to get to physics that you never had before, right? So, and this is actually what we do. We're trying to use new physics to allow these small discharges to exist, right? And to get something from very low power. Like, I'm amazed we can get thrusters operating at 1 watt. So it's only possible because we tap into new physics, or not new physics, but at least for us in the thruster community, it's new applications. So, for example, vacuum arcs, erosion. Basically, it's a thruster that eats itself. It's something that you would like to avoid in a big thruster. You basically have to maybe it's like something that you are trying to run away from in the big thruster is the basis of your micro thruster. So we have to change our focus. And indeed, materials is the key, are the key, because you can generate plasmas at very low power or in these pulse systems. If we consider Hall thrusters, where we're talking about bulk ionization in gaseous state, yeah, again, we know the scaling don't work, and then you have to change the geometry, like Francesca said. You're going into it. You're getting away far from the ideal concept. You have an annular device, you have a spherical device, you have a 1D device, and you start having these quirks and features important, and it's really important, because even if you change the slope of something, it changes completely the characteristics of your device. So how can you quantify that? How can you make a theory out of this? It's very hard, but we have to do it. Otherwise, we cannot have these low power devices. So I think we are in this stage of experimentation that we still don't have the theory. So there's a lot of work, theoretical work. I don't know, maybe new concepts. I think like connection of the simulation to the experiment is vital here, because the simulations allows you to go beyond 1D, and 0D models, and introduce these complexities into the equations and you are able to solve them. So tight interaction between development of the hardware and the simulation, much tighter than before, may be the key. Maybe the key for giving us new capabilities.
Totally.
Yeah, maybe I spoke too much.
Totally agree with you. No, totally agree with you. So, and Patrick, please give your contribution.
I definitely concur with my learned colleagues before. Surface chemistry, surface geometry, surface interactions are very important. The arc thruster I'm working with, it derives from a surface material, thin film deposition, surface modification, surface chemistry modification device used for decades. So by its nature, it not only interacts with the surfaces inside the discharge volume and within your test chamber as well, it modifies them. Whereas with a lot of the gas flow systems, you're quite right to worry about ion sputtering and erosion of the discharge channel. If you're using a material that is depositional, for example, if you're using titanium on the inside of as you discharge cathode in an arc thruster, you need it to deposit on the insulator between whatever triggering electrode you have, whether you're using the triggerless thermionic system and it needs to go over an annular insulator or any other method. You need good deposition and good adhesion in order to keep building that up. And not all materials will do this. You will also get conformal coatings of your cathode material on the interior of your anode. You need to select the right material for this because it's a depositional plasma. You keep building stuff up. You get ion deposition, even ion implantation, you wind up forming effectively a functionally graded composite of a nanoscale. But you select things right, and you can make sure that the layer does not adhere very well as it gets thicker and thicker. With increasing thickness, you get more surface energy mismatch, and it flakes off, leaving you the right geometry. So it is, to an extent, self-healing, then self-harming, then self-healing. But you need to get this balance working. I don't have a lot of experience with gas-fed propulsion systems, but I imagine a lot of the surface chemistry is different simply because of the species you're using. Some of those species would have application in the reactive deposition systems. For example, if you want to put down a titanium nitride film, not only do you need to get your titanium there, but you need to get your source of nitrogen. One source is ammonia, not common in the Earth's atmosphere. Similarly, oxide films, best one for that is oxygen. Dominant species at low Earth orbit altitudes is atomic oxygen. So some of the functional coating community research would be critical. There are a wealth of people out there who do this for a living and are very, very good at it. And it's probably worth wandering down to the industrial coating conferences and, you know, hanging out the back of the talks and then finding the right people to talk to.
Okay. Yeah. Thank you. So finally, I'd like to have, Laurent, your point of view from the simulation side about the possible physical mechanism typical of microtrusters that we probably need to investigate more.
Yeah, so but I mean, you talk about a lot of things before. Just to I agree from what you have said. So, but as Stefan said, also it depends, I would say, on the concept you are interested in modeling. But what we can expect, for example, in all thruster, for small size all thruster, it seems we can reasonably think that secondary electron emission, for example, as far as you have a small size all thruster that can make maybe can play a major role or a higher role than in the case where you have a large scale all thruster, I would say. But it's not obvious because in parallel you have this in all thruster again, we have this anomalous transport, okay, that makes the transport of electrons across the magnetic field. And if this one is maybe higher, maybe in comparison with the role of walls, maybe also could be reduced just in comparisons. So the point is that's very difficult, I would say, to separate one problem to the global problem. And what we do, if you want to understand all these phenomena, I mean, from my point of view, is that most of the time we are all obliged to simplify the problem. And by simplifying the problem, at the end, we can ask the question: what is the link with a real, thruster that you are looking at? But it's a way just to understand step by step all the interaction and all the phenomena that take place, for example, in all thruster. But it's very difficult to even if we can have a kind of I would say the kind of list of phenomena we have to consider, and by order. Okay, it's important like this one and this one and this one. But from our heritage for a higher power all thruster, big all thruster, maybe this heritage is wrong, and we have now to reverse all the things inside our list. But to do that, and I think that the panel is here for that. We need some cross validation with experiments, and just to and maybe can we in experiments sometimes a bit simplified also the problem. just to focus on one kind of problem, just to be able just to match a bit with between numerical simulation and experiments, just to progress, I would say, in the understanding. Because as you said, the most important is the understanding of the physics that are involved in all these kind of thrusters. But I agree that now I'm starting to work a bit on vacuum arc thruster. And the physics is totally different, and I think it's maybe more difficult because now we have some scale from going from just I would say in a micrometers towards also some scale on the order of millimeters, even for small scale thrusters. So that again, it's a real that's real challenge, and that's finally what it is interesting. Is that we have a lot of things we have a lot of things to discover and just to learn, to continue to learn, just to be able just to understand that all this small size all thruster operate. But until now, I would say that people who do some prototypes and then step by step changing the materials and so on. I think that I would say that if you want to optimize the thruster, I would say now I think it's the best option at the end, because we have a lot in understanding of the physics. So I remember when I was discussing first time with Comat, who is doing vacuum arc thruster, we were thinking that a model will finally resolve all the problem, because you put everything in the model, and in the end you have a solution, and you can finally you obtain a design of. I said no. And finally they continue the prototypes, and I think that they now maybe better understand they almost can analyze what we obtain, better than only doing simulations. That's the point. Thank you.
Yeah, thank you for this point, because this is exactly what we need to link this point to the second point we want to discuss, and is related to the challenges that we have in the experimental diagnostics of microthrusters. Since I want to be a little bit provoking with the experimentalists, since I'm from the simulation side, and quite often people ask us to validate the simulation with the experimental results. But sometimes I'm asking myself, but who validate the diagnostics? Because thinking about such a small scale device, also the diagnostic itself can be very challenging, since you need really non-invasive diagnostics on this device. So I'd like to have your point of view. So I'm start again with Evgeny Raitsets. It's very challenging, right, Evgeny, to have measure, even more if we want to really understand the physics behind these small thruster. Nowadays, how is possible to have really trustable and reliable diagnostics?
Yeah, thank you, Francesco. So I in my answer, I will a little bit push back to you, because our diagnostics almost have no purpose without simulations or modeling criteria. And I think this is except performance. Performance is perfect. You don't need theory simulations. You just need orbital analysis when you will be from point A to point B. But let's say diagnostics. So as going smaller scales, you need more sophisticated diagnostics. Probes may not be possible to use because we distort plasma. So you're going to lasers. Lasers costly. So when you're getting grant for, let's say, 100,000 euro, dollars, most of your funding going to buy these lasers. And when you're doing these measurements, and then what? What are you going to do with these measurements? What's the purpose? So you know with ions now going this way, but can you actually predict what will happen if you change in cluster something? And so as a result, you know, if there is no simulations, there is no code to which experiments can be used,
Yes, okay.
there will be no justification, not solid justification for measurements, because physics is very complex. Okay, I measured what ion velocity or electron temperature like that. So what?
Yeah, I agree.
What's the conclusion?
Yeah,
so do we understand? Can we get understanding of physics just from purely empirical data? I don't think so. This is my opinion. And so therefore, you know, it's very linked together. So therefore, success of simulations will create demand in diagnostics and the development of diagnostics. So I understand, for example, your vacuum arc thruster. Actually, Michael, who joined us a little bit later, so he worked on vacuum arc thrusters for a long time, right? And now I see that there is a return of vacuum arc thrusters. And so indeed, how do you diagnose scattered spots which may actually be rotating, moving? I don't know. So it's complicated. And so what if you capture it? So what's the next? Like, what can you extract from it? Just like to be happy that you measured something? I don't think it's enough.
Yeah. Okay. Thank you. So if Michael is here, I want to know your opinion about the challenges on diagnostics on micro thrusters, generally speaking. So please, Michael.
Yeah, thanks. Yeah, I guess it's kind of. I'm pleased to see a lot of work on you know some concept, various concepts. Number one, there's a lot of different thrusters, and someone says it in micropropulsion, it's too many concepts, and I guess it's maybe just in nature of the fact that people trying various approaches and see what works the best. So this micropropulsion community still probably is infancy and in relatively to to any other probably EP approaches. So that's kind of natural that there may be too many concepts. But it's when ultimately going to really small scale, many thrusters, even so physics, as you guys saying, very different, but it actually boils down to very same problem as you all indicated of role of interaction with the solid materials and so forth, and whether it will be Hall thruster or vacuum arc thruster, if it's ultimately going to a few watts power, if that can work. So then it will be kind of coupled system. Maybe not necessarily solid material, maybe it's a liquid, so then there will be liquid propellant, but either way it will be coupled with other states, not just plasma and gas. So yeah, it's kind of one observation. The other observation, I'm really very, very pleased with a lot of efforts on what people call vacuum arc thruster. We call it a little bit differently, but it's essentially the same. Now, in that sense, it's naturally surface phenomena, right? We all understand it, but there is a lot of body of work that was done on vacuum arcs, obviously not at the same scale level in terms of current, but the beauty of vacuum arc is that it's extremely scalable. In other words, the natural size of the system is a cathode spot, right? So everything really happening in the cathode spot, and if you increase your power, increase current, so you just add additional cathode spot, which is kind of interesting. You not modify the existing spot, you just multiply, right? That's how it works. And there is a lot of mystery, regarding the cassette spot, but there is a lot of information, data, measurements. Actually, the direct sum measurement. Anders actually did, if I believe, I think Evgeny, you probably remember this paper because you review it in our seminar in Tel Aviv University.
Oh, I see.
Back in that, you actually mentioned about that.
I thought you're disclosing what I review.
No. You remember in like 1992, 93, you came to our lab and you gave a kind of review on that paper, and that was laser-based measurement of cassette spot. And the objective was to identify current density, basically size of the spot. Ultimately, because it's still kind of in dispute what is the size and how the ionization happening. Fortunately, ionization happening just in the cassette spot. Everything else is what outside is just the management of what's coming out of the cassette spot. Yeah, so the diagnostics is possible, but I think Evgeny hit a good point that if either you have to start with some kind of model, maybe analytical or semi-analytical, maybe scaling law, or simulation, and try to capture trend, and then you apply your experimental technique to validate these trends. So I would say the state of, in my opinion at least, the state of micropropulsion is such that we are still capturing trends. We may not even go into details and try to understand exactly how distribution happening in 3D scale. Kind of more important, what are the key parameters that affect specific impulse or thrust and such.
Okay, thank you, Michael, for your contribution. So I'd like to know also your experience, Igal, from the diagnostic side of the problem. So please, Igal.
Well, diagnostics, we have, I think, very good diagnostic systems for the bigger thrusters with probes, right? We have so much heritage, and this thing works and works well. And it's quite easy. I think Evgeny mentioned the costs of these laser diagnostic techniques. It's terrible. I mean, it's so costly. You give all your money to some laser manufacturer or whatever. It's crazy. We have to find some cheaper ways maybe to do optical diagnostics. This is a general comment. Regarding my experience with diagnostics of small microthrusters, vacuum arcs, for example. Well, in vacuum arcs, what diagnostics we do is on the plume, and the plume itself is it's a simple structure, right? As Michael said, everything happens in the spot. And the plume is just a collection of ions flying in some quasi-Gaussian or cosine distribution, or you modify the magnetic fields, and then it's quite traditional, like plasma lenses and things like that. So depends what you're studying. So you can study the plume. Yeah, we can do it quite easily and get good understand, and we get good results. No problem there. So depends what you want to test and understand. If you want to understand the plume, no problem, you can do it with current techniques. If you want to understand the physics of the spots, I don't know if it's necessary. Maybe you keep it as a black box. I don't know. It depends where you're starting your study and what you're trying to accomplish here. So you can do diagnostics on the plume of the thruster, and you get good understanding of the general properties of your device. And if you want to know more, first, why you want to know more? You have to be very specific for you. What are your goals? And then focus your diagnostic to these goals. So for example, in vacuum arcs, you study the plume. And as I said, you can get the entire performance. But the question is, what do you want? If you want to understand the performance, as I said, you can use the plume. But if you want, for example, to understand how the lifetime of this device is established, then you have to go to the cathode spot itself and understand the erosion and how you control erosion, and then it's surface physics, and it's a completely different topic. And unfortunately, we have, as Michael said, a lot of heritage and plasma processing community. So I think for us, the challenge is how we integrate this surface plasma physics with the plume and so on. So this is where our community comes in.
Yeah, exactly. In fact, I want to ask Paddy, do you think that in relation to what we said before, the diagnostics of the surface or the interaction of plasma surface can be relevant, can be important?
I think it can be important because with greater understanding of the processes of the cathode spot, you can possibly tune parts of your discharge. I say possibly because if the processes of the cathode spot are inherent to the technology, to striking arcs, to the material that you're actually using, you can't control it that much. As has been alluded to before, the natural size of the arc discharge is the cathode spot. If you add more current, you simply get more spots. With more spots, they then interact with each other and it becomes very nonlinear very quickly. Understanding that nonlinearity gives you better ideas on how much energy you're adding to each spot, how much is coupling across each other. We know by looking at different levels of current at different times of the pulse, we have different charge states, you have different ionization fractions, and how this changes and evolves as a discharge moves through time. Getting those better diagnostics would allow the simulations to evolve and become better as your one hand washes the other, and then we use both hands to wash our face. Getting those measurements, that's going to be hard. Yeah. These spots are very small, they move very quickly, they're very high energy. All these things mean it's difficult to focus your spectrometer there, it's difficult to focus your laser beam there, and don't even think about putting a Langmuir probe there. Your spot will go right past it, and the very dense plasma will make it white hot and then evaporate.
Sure. Yeah, okay. So Laurent, if you want, we can move to the last line, since I mean, I need mostly your contribution, and I ask your contribution mostly on the last line, which is related to the challenges in numerical simulation, since you are probably one of the most expert in this field, and so I'd like to have your point of view. And
yes, but before talking about the numerical simulation, the challenge in numerical simulation from your previous step, you know, in all thruster, when some people have performed some RPA or LIF measurements, I mean, a bit in the near field plume. Okay, from here we found some interesting information in the model according to the position of ionization and acceleration. So it was a way somewhere just to determine some properties of the plasma inside the channel. While I understand that in the vacuum arc thruster, if you have some information from the plume, it's more difficult, you know, to do the link with what happened inside the I mean, close to the cathode and inside your thruster. So that makes more difficult the relation between. While again in all thruster, it was possible to even validate model and so on, to take some useful information, I would say, from the plume. So that's the main difference.
Yeah, sure. This is due to the link between ionization and acceleration that you have in the old thruster, and you can benefit from the ion distribution function into the plume, and you can reconstruct the physics inside the channel. Sure. Yes.
So now concerning the challenge in numerical simulations.
Well, let me just introduce. I mean, probably we from numerical simulation side, probably we are more lucky. working on microtrusters since, let's say, they go in the direction of affordable problems, since probably reducing and scaling down, sizing down the system can help to having possible full-scale simulation of the device, so can really help in this direction. And also, I mean, I'd like to have your opinion and the opinion of the other panel due to the intrinsic size of the microthruster. Of course, the surface becomes important, so probably we need to solve the physics down to the bi-length, and probably without any quasi-neutrality hypothesis. But I mean, I'd like to know, first of all, your opinion and what we can do with the numerical simulation.
Yeah, the point is that if you think again in a world system, so you think in, for example, in a 3D simulation that maybe we can achieve for this small size all thruster. But when you take the number, just you can expect in terms of plasma density, for example, in temperature, in the case of all thruster again, I will focus on that. You see that finally it takes finally a lot of computational time. Why? Because you want to look to some phenomena, for example, briefing mode in all thruster, that finally that takes times. And just to be able just to capture this phenomena, you have to reach maybe your simulation during a few hundreds of microseconds. And at the end, it is a real challenge in terms of high performance computing machine, could be, but also in method, because even if you assume a perfect scaling, according to your high performance computing machine, it can take maybe 1 month on a typically 100,000 processor just to be able just to do a 3D simulation of a small size all thruster. So I think that a new algorithm like the sparse technique that we want to develop in Toulouse, just to reduce, meaning that we do not resolve. I mean, we reduce the number of cells that you have in your system. Can help just to prepare some 3D simulation for the small size all thrusters.
Laurent, do you think that kinetic effect can be important, or we still can use some hybrid formulation, or we can benefit from some kind of, scaling?
Yeah, but yes, but the point is that I realize that when you scale down, for example, the size of a thruster, okay, most of the time you increase the magnetic field, right? And then your heritage of what you have understood, for a given magnetic field strength, let's say, finally falls because you have changed, your magnetic field strength. So maybe so it is not so obvious to make the link, between what your heritage, what you have learned from large size, let's say, all thruster, and small size all thruster. But I think that we have to do. I'm doing some hybrid approach for for the cylindrical thruster or miniaturized all thruster. But I have in parallel, some way. I have some experiments and some way just to validate almost, velocity profile of ions by again, tune, I would say, the mobility, the frequency of anomalous transport. Okay, so you still have the same, I would say, the same problem. But if you have again in parallel some experiments, some experimental results that give you some order of magnitude of current and, for example, ion energy suction function, then you can finally are able just to determine some plasma properties. But I agree that it's a bit you have to do some improvement in terms of maybe yes, and plasma wall interaction, for example, or this, and then the assumption of quasi-neutrality is a bit sometimes maybe a bit strong, but.
I'd like to have your opinion about the implementation of this new algorithm based on machine learning, and what is your opinion? Are useful, trustable? We can, in fact, benefit?
Yeah, I think my own feeling from that is that, I mean, as a scientist, I don't like to use this kind of, because this means that, yes, it's more and more empirical. Okay, so for people who are not familiar with that, the point is that what you do a lot of, you change your parameters. For example, I don't know, mass flow rate, density, magnetic field, and voltage. And if you have enough money, you do a lot of experiments here, and from that point, you are using your the machine learning just to do, and from here it seems that you can capture, and this method is able just to determine as a return some anomalous transport coefficient that can put maybe in your model. But as a scientist, I mean, I don't. It's more and more. It becomes more and more empirical. But I know that we have some colleague. I think it's Ben Jones, no, at the University of Michigan, who has a lot of some funding just to work on that. But I think it's the beginning. So now we need maybe his return, and just to better understand if we can only at the end, if we can take some advantage of that approach. But I would say it's the beginning. So yeah, that's. But I think that I mean, Ben Jones, yes, he's thinking a lot of. He's thinking that this method is very promising, let's say.
Beautiful. So I like to know if the other member of the panel can want to contribute. Otherwise, I will ask Laurent if there are questions from the audience. But please, if first, if the other member want to give some contribution on the numerical simulation part, please, you are free.
Patrick?
I'd like to say that I have been agog at all the very cool things I've seen coming out of particle and cell simulations, collisional or otherwise. They have been very good at replicating some of the really complicated flows that can happen in arc thrusters, because you've got the transition between the very dense region of the spot through where it is dense enough to be collisional out into a non-collisional plume where everything has frozen out. And they have, the colleagues I have worked with on this have provided excellent guidance for what experimental tests would be of good value. So it's, that the iterative conversation needs to continue along these lines. I only wish I could give the simulations people more and better data about what's happening in the very dense and interesting part of the arc.
Okay, so well, I think that it's 6 already. So Laurent, we have time for question. We have a question from audience. First of all, since I don't see. Hello, Laurent.
Okay, so in the audience, yes.
Okay, please, could you read or give the floor?
Yeah, but nobody. Let me check. No question, no comment from the audience. Yeah.
Okay. So Laurent, if not, we can stop and end the roundtable session.
Sorry, there is one.
Oh, okay, please.
Yes. Jacek?
Okay, so is it okay?
Yes, we hear you.
finally, I just only one comment, but why these microclusters are so attractive for many people, for very small laboratories, because they seems to be not so expensive than others seems to be. And if we'd like to apply any kind of very sophisticated diagnostic, it would be impossible for such small laboratories, entities like students, clusters, to apply even such sophisticated diagnostics like Thomson scattering, which can detect instabilities, and these are valuable for our notion about anomalous transport. So it seems to me the problem is how we can translate the data of very simple diagnostic for performance of the smallest, these microclusters, and how with this data we can control the performance of those clusters. Okay, it's just my comment.
Thank you.
Okay, thank you, Jacek. Someone want to comment or?
I'll give it a go. Australia was the third nation to launch a spacecraft from its own territory. Admittedly, that was with a rocket we got surplus from the United States, and we were actually the 7th launching state of the world. But if you want to cut hairs finely enough, then it was the Soviet Union, United States, and then Australia. But that was 1967. Australia hasn't done a lot in space since. Australians themselves as individuals have been involved in a lot of things, but there hasn't been a lot of budget for space research, especially space hardware research in Australia. So trying to get in and doing things, we've got to pick the right sort of scale. So these small propulsion projects that are done as side projects around other grants in a bunch of universities, that's a lot of what we can actually do. That is where the propulsion system I've been working on, that's where that began. Thankfully, we've been able to keep it running and keep it going. And by doing a whole lot of reading of the literature of what the deposition community and the propulsion community have been doing with ARCs, and a lot of discussions with people who've been working with ARCs for 10, 20, 30 odd years, you're able to get enough of an understanding of what is known scientifically and enough of a feel for the art of ARCs to get interpretations which you then confirm with directed experiments to try and drive better empirical measurements and determinations. So you're very right in that the small micro propulsion systems, it's what small labs, small teams, small countries without a lot of space history, it's what we do so that we can get in the game. And because we get in the game to play the game, we then work hard to try and get our skills good enough so that we can contribute to the community.
Okay, thank you. And Laurent,
Yeah.
Are there some other comment or questions from audience?
No, not yet. No.
Okay. So thank you. I'd like to thank the member of the panel for this interesting discussion, and hope to see you and having discussion in person next time. And so the roundtable session is closed. Okay. And please, Laurent, if you need to.
Okay, so thank you, Francesco.
You're welcome.
Thank you for animation. So we meet tomorrow morning at 9:20. Okay, for the first talk of the Friday session. Okay, thank you to all of you just for the participation, and see you tomorrow.
Okay.
Bye bye.
It was good to see you. Bye bye.
Ciao, ciao.